There was a time when strange oceans swallowed entire continents, when the skies were ruled by dragon-sized insects, and when towering volcanoes reshaped the land in the blink of an eye. This was a prehistoric Earth. Between 500 and 66 million years ago, our planet was a shifting canvas of evolution and chaos. Giant trilobites scuttled across the seafloor long before the first dinosaur ever roared. Supercontinents like Gondwana and Pangaea formed and split apart in slow-motion continental collisions. Lush fern jungles once covered polar regions, and deserts bloomed where oceans had drowned the land. Every era brought new life forms, some bizarre, some beautiful, many destined for extinction. Before we begin this prehistoric ride, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below and settle in for a fascinating journey. The Cambrian period was the very first chapter of the Paleozoic era, and a major part of the Phanerozoic eon, the era in Earth's history when life truly began to flourish in visible and complex ways. This period lasted for about 51.95 million years, starting around 538.8 million years ago and ending around 486.85 million years ago, when the Ordovician period began. Back then, Earth looked very different. Most of the land masses were grouped in the southern half of the planet and surrounded by an enormous ocean called Panthalassa. Meanwhile, a huge supercontinent called Gondwana was coming together. As its pieces collided and fused during the Ediacaran and early Cambrian times, the movement of Earth's plates created new mountain building zones and volcanic activity along the edges. These changes helped raise global temperatures. At the same time, another landmass named Laurentia sat along the equator, separated from Gondwana by the widening Iapetus Ocean. But the most remarkable thing about the Cambrian was what happened to life itself. Before this period, most living things were tiny, single-celled creatures, and their fossils are extremely rare. Some complex multicellular organisms had started to appear toward the end of the Ediacaran, but during the Cambrian, something extraordinary occurred: the Cambrian explosion. This was a sudden burst in the variety and complexity of life, giving rise to the first members of nearly all major animal groups we know today. What also makes the Cambrian stand out is its many Lagerstätten, special fossil sites where not just hard shells, but even the soft parts of organisms were preserved. These deposits give us rare and precious snapshots of early life in exceptional detail. The word Cambrian comes from the Latin version of the Welsh name for Wales, Cymru. It was in Wales that rocks from this time period were first seriously studied. In the year 1835, geologist Adam Sedgwick gave the Cambrian its name and divided it into three parts: lower, middle and upper. He worked with fellow geologist Roderick Murchison to draw the boundary between the Cambrian and the overlying Silurian layers. At first, they agreed. But this agreement did not last. Because early Cambrian rocks didn't have many fossils, Sedgwick relied on the types of rock to define his Cambrian layers. Meanwhile, Murchison found more fossils in Silurian rocks and used these to make connections across Europe and Russia. As scientists began to find fossils in older rocks, Murchison pushed the Silurian boundary downward into territory Sedgwick claimed as Cambrian. This led to a scientific tug-of-war between their camps. Things got more complicated in the year 1852, when new fieldwork showed a clear break or unconformity within the Silurian rocks. This difference in fossil types allowed Sedgwick to reclaim some of that territory for the Cambrian. Still, the disagreement continued long after both men had died. Finally, in the year 1879, geologist Charles Lapworth stepped in. He proposed that the disputed layers belonged to a new period altogether, which he called the Ordovician. The term Cambrian was formally accepted in 1960 at the 21st International Geological Congress. It now only includes what Sedgwick originally called the Lower Cambrian, though it reaches into even older rocks today. To make global comparisons, geologists use a system called Global Boundary Stratotype Section and Point, GSSP. These are specific locations around the world where the start of a geological time unit is clearly recorded in rock layers. The Cambrian period is now divided into 4 major segments, called series, and 10 smaller divisions, called stages. At first, scientists thought the Cambrian began when trilobites, the ancient armoured ancestors of modern arthropods, first appeared. However, they later discovered small shelly fossils and ediacaran organisms that came even earlier. This led to the need for a more precise starting point for the Cambrian. It wasn't until 1994 that the Cambrian period was officially defined. Scientists chose a site called Fortune Head in Newfoundland, Canada. The base of the Cambrian there is marked by the appearance of a fossil named Treptichnus pedum, a type of burrow that represents more complex animal behaviour. Early estimates dated the beginning of the Cambrian to about 570 million years ago, but newer and more accurate dating methods now place it at 538.8 million years ago, with a margin of error of about plus or minus 0.6 million years. This date comes from ash layers in Oman, which also show a drop in carbon-13 levels and the disappearance of signature ediacaran fossils like Clodina and Namacalathus. However, some researchers argue that this site may not mark the true boundary and prefer slightly older estimates of 544 to 542 million years ago. In Russia, many paleontologists prefer to set the Cambrian's beginning at the start of the Timoteian stage, marked by the rise of mineral skeletons and the first Archaeocratan reefs. There were 4 parts of the Cambrian period: Terranuvian series, 538.8 to about 521 million years ago. This is the earliest chapter of the Cambrian. It contains no trilobite fossils. It includes the Fortunian stage and an unnamed stage 2, characterized by trace fossils and small shelly fossils. The name Terranuvian was made official in the year 2007. Cambrian Series 2, about 521 to 506.5 million years ago, not yet officially named. It includes Cambrian Stage 3 and Stage 4. This period saw a burst in animal diversity, especially in trilobites and archaeochiaths. Global comparisons are hard due to regional differences in fossils. Meolingian series, about 506.5 to 497 million years ago, formerly called Cambrian Series 3. It includes the Wooluan, Drumian, and Gujangian stages. It was approved in 2018 and is named after the Miaoling Mountains in China. This period begins with the appearance of the trilobite Eryctocephalus indicus. At the boundary between Series 2 and the Meolingian, many trilobite types, like Alanellids, Eodicids, and Redlicaids, went extinct. This is considered the first known mass extinction of trilobites. Phrongian series, about 497 to 486.85 million years ago. This is the final segment of the Cambrian. The name was approved in 2003 and replaced the older term Upper Cambrian. It begins with the appearance of the trilobite Glyptonostus reticulatus. It includes the Paibian stage, the Jiangshanian stage, and an unnamed stage 10. The Cambrian Ordovician boundary is officially marked at Greenpoint, in western Newfoundland, Canada, and dated to 486.85 million years ago. This point is defined by the appearance of a tiny tooth-like fossil called Epetognathus fluctivagus. In areas where this fossil isn't found, scientists use other markers, such as planktonic graptolites or the trilobite Jujujaspis borealis. Several major meteorites struck Earth during the Cambrian. Around 535 million years ago, a large impact created the Nygren crater in Estonia, which is about 20 kilometers wide. The Gardnos crater in Norway, about 5 kilometers wide, formed around 500 million years ago in a shallow sea. During the Cambrian period, the Earth's climate was mostly warm and humid. Scientists know this because of the kinds of sediments and rock formations found from that time. These include tropical carbonate platforms, reefs built by ancient sponge-like creatures called archaeocyathans, deposits of bauxite, which forms in warm, wet climates, and minerals like evaporites and calcretes that are typical of dry, arid zones. The wide spread of these features, especially in tropical areas stretching across many latitudes, tells us that the Earth was in what scientists call a greenhouse climate, a time when there were no major ice sheets, and temperatures were consistently high across much of the planet. Toward the end of the Cambrian, fossil evidence from trilobites, extinct marine creatures with hard shells, suggests that there was only a gentle temperature difference between the poles and the equator. In other words, even the polar regions weren't extremely cold, showing how evenly warm the Earth was. Some scientists have found signs of ancient glaciers in the Avalonia region, which was located in high southern latitudes at the time. But there's still debate about whether those icy sediments were actually formed in the Cambrian or in the slightly earlier Neoproterozoic period. When it comes to measuring how hot the Earth really was during the Cambrian, the results vary depending on the method used. Some estimates suggest that the global average temperature may have been over 40 degrees Celsius. However, more reliable models that pull information from multiple sources give more moderate temperatures, around 20 to 22 degrees Celsius at the very beginning of the Cambrian, rising to about 23 to 25 degrees Celsius for the rest of the period. This long-lasting warmth was strongly tied to high levels of carbon dioxide in the atmosphere. A major factor in this was the assembly of the massive supercontinent Gondwana. As landmasses came together, Earth's tectonic plates shifted and formed new boundaries where volcanic activity occurred. These volcanic eruptions released large amounts of greenhouse gases like carbon dioxide, which further warmed the planet. In particular, a huge volcanic event known as the Calcaringi Large Igneous Province erupted around stage 4 of the Cambrian and continued into the early Meolingian. These eruptions poured enormous quantities of carbon dioxide, methane and sulfur dioxide into the air, causing sudden changes in climate and raising sea surface temperatures significantly. However, there is still a lot of uncertainty about exactly how hot the oceans became. Scientists try to figure this out by studying oxygen isotope levels in ancient marine rocks. But there's ongoing debate over what those values really mean when comparing Cambrian oceans to other times in Earth's history. Depending on which estimates you look at, tropical sea surface temperatures during the Cambrian may have ranged from 28 to 32 degrees Celsius, or even from 29 to 38 degrees Celsius. By comparison, today's average tropical sea surface temperature is around 26 degrees Celsius. While temperatures soared, atmospheric oxygen levels were still quite low compared to today. Oxygen had been rising steadily since the Neoproterozoic period, thanks to the growth of photosynthesizing organisms in the oceans. But during the Cambrian, oxygen levels in the atmosphere fluctuated between about 3% and 14%, far below the modern level of about 21%. The combination of low oxygen in the air and high temperatures in the oceans meant that less oxygen could dissolve in seawater, especially in deeper regions. This led to anoxic conditions, where deep parts of the ocean were almost entirely lacking in oxygen. These low oxygen environments had a big impact on marine life and the evolution of early animals. As new kinds of organisms began to burrow into ocean sediments, they mixed up the layers of mud and exposed deeper, oxygen-poor materials to the oxygen-rich waters above. This process, known as bioturbation, actually reduced the burial of organic carbon and sulfur in the sediments. Over time, this made it harder for oxygen to build up in the atmosphere and oceans, contributing to more widespread oxygen shortages underwater. On the other hand, when the continents experienced high rates of weathering, the breakdown of rocks due to wind, rain and other natural forces, more nutrients flowed into the oceans. This sudden burst of nutrients led to a bloom in phytoplankton, tiny photosynthetic organisms that form the base of the food chain. Their explosion in numbers helped fuel the evolution of more complex animal life. But when these plankton blooms happened too quickly, they caused eutrophication, a process where too much organic matter is produced and later decomposes, consuming oxygen and leaving waters severely depleted of it. These cycles of rising and falling oxygen levels shaped life on Earth in powerful ways. Whenever oxygen levels rose, biodiversity increased. More oxygen supported more active lifestyles, bigger body sizes, and more complex ecosystems, as oxygen-rich conditions expanded the habitable seafloor. But when oxygen levels dropped, due to changes in sea level, shifts in ocean currents, or upwelling of deeper, low-oxygen waters, many animals could not survive. These low-oxygen events led to mass extinctions, sometimes in specific regions and other times across the globe. All in all, the Cambrian period was a time of dramatic environmental ups and downs. These swings, between oxygen-rich and oxygen-poor conditions, played a major role in driving evolutionary innovation, causing some species to go extinct and pushing others to adapt in new and remarkable ways. As for plant life, there wasn't much on land during the Cambrian. The plants of the sea didn't look very different from those that existed just before, during the Ediacaran period. The main types were large algae, including forms named Fucsianospira, Cinna and Marpolia. Interestingly, no calcareous, calcium carbonate-containing algae have been found from this time. There are no fossils of land plants, what scientists call embryophytes, from the Cambrian. However, microbial life thrived on land, especially in the form of biofilms and microbial mats that covered tidal flats and beaches as early as 500 million years ago. These microbial communities played a role similar to modern-day soil crusts in deserts, helping stabilize the ground and contributing to the early formation of soils. Although some molecular clock studies suggest that land plants may have first evolved during the Middle or Late Cambrian, this idea remains controversial. What is clearer is that the large-scale removal of atmospheric carbon dioxide by these plants through a process called carbon sequestration didn't truly begin until the Ordovician period, which followed the Cambrian. Some researchers also think that arthropods, creatures like insects and spiders, may have started to move onto land during the Cambrian, based on genetic evidence. But like land plants, the oldest definite fossils of land arthropods also appear in the Ordovician, making their Cambrian origin uncertain and still a topic of debate. The Cambrian explosion was a time of extraordinary change and growth in the history of life on Earth. It happened roughly 541 million years ago, marking the beginning of a new chapter when life became more complex and diverse. During this period, many different types of animals developed rapidly, especially those with more than one cell, what we call multicellular life. Most creatures that lived during the Cambrian period lived in the ocean. For a long time, scientists believed that trilobites, a kind of ancient sea creature with a hard shell, were the most common animals of the time. But newer research has shown this wasn't exactly true. Trilobites were certainly important, but they were only one part of a much larger group called arthropods, a group that includes insects, crabs, spiders and others. In the Cambrian seas, arthropods were the real rulers, but many of them had soft, fragile bodies that didn't fossilize easily. Trilobites, on the other hand, had strong armor-like shells made of calcium carbonate, a substance similar to what makes up seashells. These shells preserved well in the fossil record, making trilobites seem far more common than they actually were. This period marked a turning point for life on Earth. A dramatic increase in the number and types of species occurred. But not all life forms made it through this transition. The Ediacaran biota, soft-bodied organisms that lived before the Cambrian, suffered a mass extinction. Around the same time, new animal behaviours appeared, especially burrowing into the seafloor. These burrowing creatures changed the ocean floor in ways that could not be undone. Before this, the seafloor was mostly covered by thick microbial mats, like slimy blankets of microorganisms. But as animals dug through the seabed, they disrupted and eventually destroyed many of these mats in a process called bioturbation. This forced the creatures that relied on the mats either to adapt or die out. Those that could adjust began to take advantage of the new types of habitats that formed in the disturbed seabed. During the same period, animals with hard, mineralized body parts, such as shells, began to appear more frequently. These included representatives from most of the major groups, or phyla, of animals that we still recognize today. One example is the bryozoans, tiny colonial creatures that were once thought to have appeared much later, in the Ordovician period. But most of these early animals were only primitive ancestors of today's forms, and since animals with mineralized bodies usually lived on the sea floor, they didn't fully represent the diversity of soft-bodied life that may have been far more abundant. Even though the early Cambrian period was a time of incredible growth, earning it the name Cambrian explosion, this boom didn't last forever. Around 515 million years ago, things began to change. The number of species going extinct started to outpace the number of new species appearing. About 5 million years later, the total number of different genera, a way of grouping related species, dropped from around 600 to just 450. The rate at which new species were forming fell to as little as 1/5 or 1/3 of what it had been earlier. By around 500 million years ago, oxygen levels in the oceans dropped sharply. This caused hypoxia, a situation where there isn't enough oxygen for most animals to survive. At the same time, levels of hydrogen sulfide, a toxic gas, began to rise. a dangerous combination that led to yet another extinction event. The second half of the Cambrian period turned out to be much quieter and less biologically rich than the first. Several quick waves of extinction occurred. Reef-building sponges called Archaeochyartha, which had taken over from older reef-forming organisms like stromatolites, eventually died out too. After their disappearance, stromatolites made a brief comeback, but overall biodiversity remained low until the Great Ordovician biodiversification event, which brought another explosion of life later on. Life in the Cambrian oceans wasn't easy. Oxygen levels were often low and unpredictable. When deep ocean waters that lacked oxygen occasionally rose up into shallower areas, a process known as upwelling, entire communities of organisms could be wiped out. Yet these stresses also pushed evolution forward, eventually leading to greater biodiversity. Interestingly, some Cambrian animals even started to explore the land. Fossils of their movement, known as trace fossils, have been found. Two of these are called protichnites and climactic snites. Scientists believe that at least some of the protichnites were made by an extinct type of arthropod called a euthocarcinoid. As for climactic knights, no fossils of the creature that made them have been discovered yet, but the tracks and resting marks they left behind suggest a large, soft-bodied creature, possibly something like a giant slug or an early mollusk. Compared to later periods in Earth's history, the variety of animals during the Cambrian was still quite limited. Creatures that floated freely in the water were rare. Most animals lived on or just above the seafloor. Animals with mineralized shells or skeletons were also less common than they would become in later periods. One reason for this was the chemistry of the ocean, which wasn't ideal for forming and preserving hard parts. Despite these limitations, the Cambrian period gave us some of the most remarkable fossil discoveries ever found. Many fossils from this time preserved not just bones or shells, but also soft tissues like skin, gills, and digestive systems, things that rarely survive in the fossil record. These special fossil sites, known as Lagerstätten, give us an extraordinary window into ancient life. Some of the most famous examples include Sirius Passet in Greenland, the Sinsk algal lens in Russia, the Maotianshan shales in China, the Emu Bay shale in Australia, and the Burgess shale in Canada. The Ordovician period was a fascinating chapter in Earth's ancient story. It was the second period of the Paleozoic era, and also the second of 12 major periods that make up the Phanerozoic eon, the long stretch of time that includes most of Earth's complex life. The Ordovician lasted for around 41.6 million years, beginning about 486 million years ago, right after the Cambrian period ended, and coming to a close around 443 million years ago, when the Silurian period began. The name Ordovician comes from the Ordovices, a Celtic tribe that once lived in what is now Wales. The period was officially named in the year 1879 by a British geologist named Charles Lapworth. At the time, there was a disagreement between two other geologists, Adam Sedgwick and Roderick Murchison, over which period certain rocks in northern Wales belonged to. Sedgwick said they were from the Cambrian, while Murchison claimed they were from the Silurian. But Lapworth noticed something important. The fossils in those rocks were different from both the Cambrian and the Silurian, so he proposed a brand new period, the Ordovician, to settle the debate. It wasn't until the year 1960, about 40 years after Lapworth had died, that the International Geological Congress officially accepted the Ordovician as a recognised geologic period. During the Ordovician, life in the oceans didn't just survive, it flourished. The great explosion of life that began during the Cambrian kept going strong. The oceans were teeming with invertebrates, especially mollusks and arthropods. Arthropods were particularly important during this time, and some of them may have even begun to move onto land, though they wouldn't become fully established there until the Devonian period, which came later. This period also saw the very first land plants, small and simple, but a sign of great things to come. One of the most exciting developments was the Great Ordovician biodiversification event, a time when the variety of life forms dramatically increased. It was also during the Ordovician that fish, the world's first true vertebrates, began to evolve, and there's evidence that fish with jaws may have first appeared toward the end of this period. Something very unusual also happened in the sky. During the Ordovician, Earth was bombarded by about 100 times more meteorites per year than we experience today. This strange phenomenon is called the Ordovician meteor event, and some scientists believe it might have been caused by a ring system that briefly formed around the Earth. The climate of the early Ordovician was extremely hot. Earth was in a greenhouse state, with sea surface temperatures as high as those during the early Eocene climatic optimum, a much later warm period. At the beginning of the Ordovician, the atmosphere had very high levels of carbon dioxide, but then things began to change. By the later part of the early Ordovician, the planet started to cool down, entering a more temperate phase during the middle Ordovician. Eventually, the Earth entered a long icy phase known as the early Paleozoic Ice Age. This cold period may have started as early as the Florian Age, or perhaps a little later during the Darwinian or Cambrian stages. During the Dipingian and Cambrian, there were also periods of heavy rainfall, as seen in metal traces from ancient rocks in the region now known as Baltoscandia. Then, during the early Catian, temperatures rose again briefly in an event called the Boda event, which led to the formation of reef-like structures and the rapid spread of marine life across what is now Europe. Another rainy phase also happened during the early Catian. Afterward, Earth cooled again, and this eventually led to a major glacial period called the Hernantian glaciation, which happened at the very end of the Ordovician. During this time, sea levels were higher than at any other time in the Paleozoic era. The continents were mostly low-lying and flat, so vast areas were flooded by shallow seas. These shallow waters encouraged the growth of many kinds of marine creatures, especially those that built hard shells or skeletons out of calcium carbonate. In the early Ordovician, sea levels kept rising, staying high through the middle of the period. Although there were some local drops in sea level, the overall trend remained upward into the early late Ordovician. Then, as the Earth grew colder in the few million years leading up to the Hernantian glaciation, sea levels began to fall steadily. During the glacial period itself, sea levels rose and fell multiple times, but the exact details are still not fully understood. Some scientists think that sea levels began fluctuating even before the Hernantian glaciation officially began, but solid evidence of glaciers does not appear until the very end of the period. There is now proof that glaciers formed during the Hernantian on what are now Africa and South America, which were located near the South Pole at the time. These southern lands helped form the icy caps of the glacial age. Much like North America and Europe, the giant southern continent called Gondwana was mostly covered by shallow seas during the Ordovician. These warm, sunlit waters were perfect for life that needed space to grow and build reefs or shells. The enormous Panthalassic Ocean stretched across most of the northern hemisphere, while several other ancient seas and oceans also existed, including Prototethys, Paleotethys, the Canti Ocean, which eventually disappeared by the end of the period, the Iapetus Ocean, and a newly forming sea called the Reich Ocean. During most of the late Ordovician period, life in the oceans was thriving. Many kinds of marine animals were doing well, and ecosystems continued to grow more complex. But as the period drew to a close, something dramatic happened. A series of major extinction events struck, wiping out many creatures that had once filled the seas. Tiny tooth-like animals called conodonts and floating organisms like graptolites were hit hard. Two entire groups of trilobites, Agnostida and Tychoparida, disappeared completely, while another group called the Asaphida shrank to only a small number. Other sea animals such as brachiopods, which looked like clams, bryozoans, which formed coral-like colonies, and echinoderms, relatives of starfish and sea urchins, were also badly affected. A type of squid-like creature known as the endocarid cephalopod was almost completely wiped out, surviving only as rare forms in the next period, the Silurian. Scientists believe that this great die-off may have been caused by a sudden ice age at the end of the Ordovician. This cooling was possibly triggered by the spread of the first land plants, which changed Earth's climate by pulling carbon dioxide out of the atmosphere. The final part of the Ordovician became one of the coldest times in the last 600 million years of Earth's history. Despite the extinctions, the Ordovician period gave rise to a wide variety of new marine life that would shape the rest of the Paleozoic era. The oceans were filled with layers of animals that filtered tiny particles from the water for food. These animals formed simple food chains and lived in tightly connected communities. Life during the Ordovician was far more varied and complex than in the earlier Cambrian period, and this pattern of ocean life has continued in many ways all the way to today. One of the most incredible events of this time is called the Great Ordovician Biodiversification Event. It may not be as famous as the Cambrian explosion, but it was just as important. During this time, the number of marine animal genera increased by 4 times, making up about 12% of all known marine life in the Phanerozoic eon. Many animals also became smaller than their Cambrian ancestors, and filter-feeding organisms became more common than ever before. By now, the old sea life from the Cambrian, like inarticulate brachiopods, archaeocyathids, eocrinoids, and early trilobites, was being replaced. Taking their place were articulate brachiopods, which had hinged shells, crinoids, sea lilies, and many types of cephalopods, relatives of modern squids and octopuses. Articulate brachiopods especially began to take over the ocean shelves, replacing trilobites in many places. These changes reflected a big increase in animals that made hard, shell-like coverings from carbonate minerals. The layout of the continents during the Ordovician also had a big effect on what kinds of animals evolved. Different areas developed their own unique types of invertebrate life. For example, the continents of Laurentia and Baltica, which were near the tropics and surrounded by shallow, warm seas, had their own kinds of trilobites, different from those found in Gondwana. Gondwana itself had separate animal groups in its warm and cooler regions. Parts of Central Asia, like the Tian Shan area, were closely related to Gondwana in terms of life forms. The Alborz region of what is now Iran also shared connections with South China. Southeast Asia's sea life had strong ties to Gondwana as well. North China shared similarities with both Laurentia and parts of South America that were part of Gondwana. There was even a unique group of animals living in what scientists call the Celtic province. However, some animals, like the tropical articulate brachiopods, lived all over the world and weren't limited to just one region. As the Middle Ordovician began, the spread of marine animals across the world increased. As a result, faunas became less provincial, meaning they were more widely shared between regions, especially as oceans like the Iapetus Ocean grew smaller. Still, differences in marine life between areas continued up until the end of the Ordovician. Trilobites, those armoured sea creatures with jointed legs and many eyes, were especially abundant and diverse. They evolved rapidly during the Ordovician and developed all sorts of strange features. Some grew long spines and bumps to protect themselves from predators like early sea scorpions, eurypterids, and predatory cephalopods. One trilobite called Aglena prisca even learned how to swim. Others developed wide snouts for digging through ocean mud. A group known as the trinoclades had strange, flat, pitted borders around their head shields. Some trilobites, like Asaphus kowalewski, grew long stalks on their eyes to help them see predators from a distance, while others lost their eyes completely. By the end of the Ordovician, early arachnids, relatives of spiders and scorpions, may have started making their way onto land. Although single coral animals had existed since at least the Cambrian, large reef-building corals appeared during the early Ordovician, along with the first known soft-bodied octocorals. This increase in coral reefs also meant there were more animals that used calcium to build shells and skeletons. Brachiopods became incredibly diverse, adapting to nearly every marine environment, from shallow shores to deeper waters. Even after the great biodiversification, they continued to evolve quickly. Mollusks, which had first appeared either during the Cambrian or possibly even earlier in the Ediacaran, also became more common and came in many shapes and sizes. These included clams, bivalves, snails, gastropods, and straight-shelled cephalopods called nautiloids, which spread from shallow tropical seas to nearly every part of the ocean. Graptolites, tiny colonial animals that floated in the ocean, thrived throughout this time. A particular group called Nemograptus gracilis became widespread during a period of especially high sea levels in the Sandbian Age. New types of crinoids and cystoids, ancient echinoderms, also appeared. Although scientists used to believe that the first real fish appeared in the Ordovician, fossil discoveries from China now show that jawless fish, ostracoderms, likely already existed in the early Cambrian. The very first jawed fish, gnathostomes, may have started to appear during the late Ordovician. tiny flask-shaped microfossils known as Chitinozoans, which first showed up in the late Woolluan Age, went through a huge boom in the early part of the Ordovician, the Tremodocian, quickly spreading across the globe. Several animals during this time also formed partnerships called symbiosis, where different species lived closely together for mutual benefit. At the beginning of the Ordovician, trilobites were joined by many new kinds of sea creatures. These included tabulate corals, many new types of brachiopods like strophomonids and rhynchonellids, branching bryozoans, floating graptolites, conodonts, and all sorts of mollusks and echinoderms. This group even included the first brittle stars, ophiuroids, and true starfish. Arthropods, the group that includes insects and crustaceans, continued to be abundant. Older trilobite orders from the Cambrian stuck around, and a new one called Phacopida emerged. The earliest evidence of land plants also appeared during the Ordovician, marking the beginning of a major change in Earth's ecosystems. In the middle of the Ordovician, ocean communities began to change, trilobites became less dominant, and ecosystems became more balanced and diverse. Brachiopods, bryozoans, mollusks, and echinoderms flourished. Corals became more varied, with tabulate corals spreading and the first horn-shaped rugose corals appearing. Planktonic graptolites continued to diversify, and a new group called the Diplograptina emerged. One of the earliest known armoured jawless fish, called Arandaspis, lived during this time. The Middle Ordovician also saw a big increase in animals that burrowed into hard materials like shells and rocks. This period is called the Ordovician Bioerosion Revolution. Scientists know this because of the sudden appearance of many boring trace fossils with names like Triponites, Paleosabella, Petroxestes, and Osprionides. Bioerosion became an important force, especially in thick-shelled animals like corals, bryozoans, and brachiopods, as well as in the vast hard seabeds made of carbonate rock that were common during this time. During the later part of the Cambrian period, and even more so in the Ordovician period that followed, green algae were already quite common. These green algae are thought to be the ancestors of the first land plants. Sometime during the middle to late part of the Ordovician, more than 460 million years ago, tiny, soft-bodied plants that looked like modern-day liverworts began to appear on land. These early plants did not have vascular systems, which means they couldn't move water or nutrients through their bodies the way most modern plants do. Fossilized spores found in Ordovician rocks are similar to those of bryophates, a group that includes mosses and liverworts today. Alongside the first land plants, some of the earliest fungi were also starting to thrive. Among them were special fungi known as arbuscular mycorrhizae, which belonged to a group called the glomerales. These fungi formed an important partnership with the early plants by attaching to their roots. In exchange for sugar from the plants, the fungi helped gather minerals from the soil and pass them to the plant cells. This kind of teamwork, called mycorrhizal symbiosis, was essential for helping plants survive on land. Fossils of these fungi, including their thread-like hyphae and tiny spores, have been found in Ordovician rocks from what is now the US state of Wisconsin. These fossils are about 460 million years old, from a time when land was mostly empty except for simple, moss-like plants and these helpful fungi. Meanwhile, in the oceans, strange structures called stromatolites, formed by layers of microorganisms, mostly bacteria, were still around, although they were far less widespread than they had been during the Proterozoic eon, billions of years earlier. By the Ordovician, stromatolites only appeared in specific, isolated places. The Ordovician period ended in dramatic fashion. A series of extinction events swept across the oceans and wiped out a huge number of living things. Altogether, these disasters make up the second largest mass extinction in Earth's entire history. Only the much later Permian Triassic extinction was worse. These devastating extinctions happened between 447 million and 444 million years ago, right at the boundary between the Ordovician and the next period, the Silurian. At that time, all complex life still lived in the sea. Nearly half, about 49% of all animal genera, were wiped out forever. Groups like brachiopods and bryozoans were hit especially hard. Many kinds of trilobites, conodonts, and graptolites also vanished. Most scientists believe that these extinctions were caused by a sudden shift to colder global conditions. The warm, stable greenhouse world of the Ordovician gave way to an ice age, starting in the late Cretaceous stage and peaking during the Hernantian stage. Glaciers began to grow and global temperatures dropped. Oxygen isotope data from fossil brachiopods suggest this ice age may have lasted for only about 500,000 to 1.5 million years. However, some studies suggest that cooler conditions didn't truly fade until well into the Silurian period. One of the key reasons the Earth cooled was a dramatic drop in atmospheric carbon dioxide. During the Ordovician, carbon dioxide levels may have fallen from about 7,000 parts per million to just 4,400 parts per million. One possible cause was increased volcanic activity, which laid down fresh silicate rocks. As these rocks slowly eroded, they absorbed carbon dioxide from the air. Another explanation is that newly evolved mosses, liverworts and lichens on land increased chemical weathering, also pulling carbon dioxide out of the atmosphere. With less carbon dioxide, the greenhouse effect weakened, and the Earth began to cool, especially in the shallow seas where most marine life lived. There's also a fascinating hypothesis that Earth may have had a ring system during the Ordovician. If such a ring existed, it could have blocked some sunlight, contributing to the cooling. In addition, a major meteor event during this time may have played a role in climate change. As the southern supercontinent Gondwana drifted over the South Pole, thick ice sheets formed on top of it. We know this from glacial features found in upper Ordovician rocks in North Africa, and in parts of what is now northeastern South America, areas that were near the South Pole during that time. As the glaciers expanded, sea levels dropped dramatically. Shallow inland seas that once teemed with life drained away, destroying many marine habitats. When the seas briefly returned, they brought with them smaller, less diverse communities of life. Then, with another wave of glaciation, the seas withdrew again, leading to further extinctions. This back-and-forth pattern deeply affected life in these shallow marine environments. Species that lived in only one particular inland sea were especially vulnerable. The first wave of extinction mostly affected tropical species, while the second wave dealt a harder blow to those adapted to cooler waters. Despite the devastation, some life forms managed to adapt to the new environment. During the coldest period, ocean waters became more oxygen-rich at deeper levels, allowing new bottom-dwelling organisms known as the Hernantian fauna to move in. These creatures spread widely and lived in many different parts of the world. Eventually, the Ice Age came to an end. As the glaciers melted, sea levels rose again and stayed high. With the flooding of the continental shelves came a burst of new life. Many of the surviving groups began to diversify, filling the gaps left by extinct species. Interestingly, some species that disappeared during the extinction later reappeared in the Silurian period. Scientists call these Lazarus taxa, since they seem to have come back from the dead. It's likely that these organisms survived in small hidden environments called refugia, where they waited out the worst of the changes. One alternate theory suggests that a powerful gamma ray burst from space may have hit Earth for just 10 seconds. This could have stripped away the ozone layer and exposed surface life to deadly ultraviolet radiation, leading to mass death and possibly triggering a cooling trend. More recent studies suggest that the entire late Ordovician extinction might not have been two separate events, but rather one long and drawn-out crisis. This event likely lasted several 100,000 years and involved sudden shifts in sea level and sediment patterns that caused waves of extinction. The Silurian period was a remarkable chapter in Earth's history. It lasted for about 23.5 million years, beginning at the end of the Ordovician period around 443 million years ago, and ending at the start of the Devonian period, about 420 million years ago. This period was the third out of 6 major periods in the Paleozoic era, and the third of 12 periods in what scientists call the Phanerozoic Eon, the time when visible, complex life flourished on Earth. Even though geologists have clearly marked the layers of rock that signal the beginning and end of the Silurian, the exact timing is still uncertain by a few million years. The Silurian began right after a devastating global event, one of the biggest mass extinctions in Earth's oceans. During this crisis, around 60% of marine species vanished. It marked a dramatic turning point and a new beginning for life on our planet. One of the most exciting things about the Silurian was that life began to colonize the land in earnest. This major leap is often called the Silurian-Devonian terrestrial revolution. Before this time, most life was underwater, but now plants and animals were starting to adapt to life on dry ground. Early land plants that had no roots or vascular systems began to evolve into vascular plants, which could transport water and nutrients internally and grow taller. Alongside them, new types of fungi, especially Dicarian fungi and Glomeromycotan fungi, spread and diversified, helping plants form root systems and survive in rocky, harsh environments. At the same time, three important groups of arthropods, myriapods, like millipedes, arachnids, like spiders, and hexapods, insects and their relatives, became fully adapted to life on land. This was the first wave of animals to permanently leave the ocean behind. The Silurian also witnessed an explosion in the variety of jawed fish. New groups such as placoderms, armoured fish, acanthodians, which would give rise to modern sharks and rays, and osteichthyans, bony fish, made their appearance. The bony fish later split into two types: lobe-finned fish, which would eventually lead to amphibians and humans, and ray-finned fish, which dominate the seas today. However, as these jawed fish thrived, the older jawless fish, like ostracoderms and conodonts, began to decline. The balance of power in the ocean was shifting. The Silurian period was first named and described in the early 1830s by a Scottish geologist named Roderick Murchison. He studied fossil-rich rock layers in southern Wales and decided to name the period after the Silures, an ancient Celtic tribe that once lived in the region. This naming was inspired by his friend and fellow geologist Adam Sedgwick, who had earlier named the Cambrian period after another Latin name for Wales. However, Murchison's identification of Silurian rocks in certain areas overlapped with the rocks that Sedgwick had assigned to the Cambrian. This led to a fierce scientific rivalry that ended their friendship. Eventually, an English geologist named Charles Lapworth solved the conflict by creating a new period between the Cambrian and Silurian, which he called the Ordovician. Elsewhere, some scientists used a different name for the Silurian, Gotlandian, after rocks on the island of Gotland in the Baltic Sea. The French geologist Joachim Barrande, expanding on Murchison's work, divided Silurian rocks in Bohemia, in what is now the Czech Republic, into 8 stages, though later studies revealed that some of these actually belonged to the Devonian period. Still, his work made Bohemia one of the most important regions for studying early Silurian fossils. During the Silurian, the ancient supercontinent Gondwana covered the equator and stretched across much of the southern hemisphere. Meanwhile, a huge ocean spread across the northern half of the globe. Because sea levels were very high and most land was low and flat, many small islands formed, creating all kinds of different environments for life to thrive. Gondwana continued to drift slowly southward, but the ice caps from the previous period's glaciation began to melt. This led to rising sea levels. In many places, Silurian rock layers lie directly above eroded Ordovician rocks, which tells geologists that the seas flooded back over the land. At the same time, the continents Avalonia, Baltica, and Laurentia were drifting toward the equator and eventually collided. This was the beginning of a new supercontinent called Euramerica. When Proto-Europe smashed into North America, it squeezed and folded layers of ancient sediments that had built up for millions of years. This powerful geological event is known as the Caledonian orogeny, a mountain-building phase that affected a huge area, from present-day New York State across Greenland, through Europe, and all the way to Norway. As the Silurian came to a close, sea levels dropped again. This drop left behind salty basins, evaporate deposits, stretching from Michigan to West Virginia. The freshly formed mountain ranges also began to wear down quickly. One ancient river, the Tees River, carved into older Ordovician rocks and left behind Silurian sediments in what is now northern Ohio and Indiana. In the northern hemisphere, the massive ocean called Panthalassa dominated the scene. Other seas and oceans included 2 early versions of the Tethys Ocean, the Prototethys and the Paleotethys, as well as the Rheic Ocean, the Iapetus Ocean, a narrow sea between Avalonia and Laurentia, and the newly formed Ural Ocean. The Silurian period was once thought to have been a time of calm, steady warmth. This was in contrast to the icy extremes of the Ordovician period before it, and the intense heat that followed in the Devonian period. But today, scientists know that the Silurian climate was anything but stable. In fact, the planet went through many dramatic climate shifts during this time. We know this because of major changes seen in carbon and oxygen isotopes, chemical clues left behind in rocks from that era. Sea levels also changed greatly during the Silurian. At the beginning of the period, they rose significantly from their low point during the Hernantian glaciation, then slowly dropped again toward the end. However, this wasn't a simple rise and fall. Sea levels went up and down in smaller cycles too. Scientists have identified 15 distinct high sea level periods when the ocean rose above the edges of the continents. At its highest, the Silurian sea level was likely about 140 metres, or 459 feet, higher than its lowest point. During the Silurian, Earth entered a warm, greenhouse phase. The atmosphere was full of carbon dioxide, about 4,500 parts per million, much higher than today's levels. Warm, shallow seas spread out across the tropical regions of the planet. In the early Silurian, glaciers that had once reached into the continents shrank and slowly retreated back toward the South Pole, almost vanishing by the middle of the period. The climate of this time was also marked by fierce and frequent storms. We can tell this from thick layers of coquina, rocks made up of broken shells, that were formed by storm-driven waves pounding the seafloor. The Silurian climate and carbon cycle were surprisingly unstable, showing more frequent shifts than in any other geological period. Scientists have named several of these dramatic events, such as the Ordovician event, the Mulder event, and the Lau event. Each of these was marked by a small extinction, sudden sea level changes, and sharp changes in carbon isotope levels. The creatures that lived freely in open waters, like plankton, were hit especially hard. Brachiopods, corals, and trilobites also suffered. These extinction events often unfolded quickly, in rapid bursts. Some researchers believe these fluctuations were due to repeated glaciations, but because there are few glacial deposits, like tillites, from the middle to late Silurian, this idea is still debated. Paleontologists see the Silurian as a time when life was still recovering from the late Ordovician mass extinction, a massive event that had disrupted the steady rise of biodiversity that began in the Cambrian and carried through most of the Ordovician. But the Silurian wasn't just about recovery, it was also a period of exciting new beginnings. For the first time in Earth's history, large fossils of land-based life appeared. These included small moss-like plants growing along lakes and streams, forming the first primitive forests. There were also large fungal-like organisms known as nematophytes, which lived in networks and likely had close relationships with underground fungi. This was the dawn of the Silurian-Devonian terrestrial revolution, when life slowly began to conquer the land. However, these early land organisms didn't yet have a major effect on the planet. That would come later, in the Devonian. In the second half of the Silurian, a truly important event took place: the appearance of the first vascular plants. These were land plants that had internal systems for carrying water and nutrients, a major evolutionary leap. The earliest known vascular plant was Cooksonia, a tiny plant that grew along streams and rivers. Although it was found mostly in marine deposits, it likely lived close to the water's edge. Another plant, Baraguanathia, which had needle-like leaves and branching stems, also appeared around the same time, about 420 million years ago, during the Ludlow epoch. Fossils of Baraguanathia have been found in Australia, Canada, and China, and they show a surprisingly advanced structure for such an early plant. Another early land organism, possibly a plant, was Eohostimella hethana, known from compression fossils from the early Silurian, specifically the Landovary epoch. Its chemistry is more like that of vascular plants than algae, which hints that it too may have been a land dweller. The Silurian was also home to the earliest known terrestrial animals. Fossils from around 425 million years ago on the island of Kerera show millipedes like Cambricaris obanensis and Arcidesmus. Other fossils from the Ludlow epoch, around 420 million years ago, show millipedes, centipedes, and spider-like creatures called trigonotarbids. These animals suggest that simple food chains were already forming on land, with predators feeding on smaller creatures. In 1990, a team led by Andrew Jerram proposed that there were likely many more land creatures, such as tiny grazers and decomposers, that we haven't discovered yet. Fossils from the Cowie Formation, including Cowiedesmus and Pneumodesmus, were once thought to be from the Middle Silurian, around 428 to 430 million years ago, but later studies suggest these rocks might actually be from the early Devonian. Even so, Pneumodesmus remains hugely important because it shows the earliest known spiracles, openings for breathing air, in a land animal. Underwater, life was booming again. The first bony fish, known as Osteichthyes, appeared during the Silurian. One group, the Acanthodians, were covered in small bony scales. Fish became more diverse, and for the first time developed jaws that could move, evolved from the front gill supports. The Silurian seas, especially around what is now North America, were home to eurypterids, also called sea scorpions, some of which grew several meters long and ruled the shallow waters. Brachiopods, marine animals with hard shells, were still very common. Many had survived the Ordovician extinction and adapted to stressful environments. At first, these animals lived in only one region, but later they spread out again. The most successful brachiopods were atripids and pentamerids. Atripids were quick to recover, but pentamerids took longer, not bouncing back until the Uronian epoch. Other sea creatures also flourished. Bryozoans, which form colonial structures, often lived only in specific regions and formed symbiotic partnerships with corals and stromatolites. Bivalves, like clams, were common and even began to burrow deeper into the seafloor for the first time. Chitons, marine mollusks with armoured plates, reached peak diversity in the middle of the Silurian. Hederelloids, strange colonial organisms, formed partnerships with certain corals, such as Entellophyllum. The Silurian was also the golden age of tentaculatoids, a mysterious group of small tube-shaped sea creatures. They thrived especially in Baltiscandia and spread widely during the Landovery and Wenlock epochs. Even trilobites, the iconic marine arthropods, managed a comeback. Though their diversity had dropped after the Ordovician extinction, they still did well during the Silurian, especially in the Rudanian. The Silurian also saw new kinds of crinoids, or sea lilies. Groups like the Flexibilia, which had survived the extinction with little harm, became more common. Monobathrid camrets diversified early, while others like cyathocrinids and dendrocrinids expanded later. An odd group called Siphocrinoids appeared suddenly near the very end of the Silurian and vanished just as quickly. Symbiosis was everywhere. Corals and stromatoporoids, reef-building sponges, often had endobiotic symbionts living inside them. Rugose corals in particular were frequently encrusted with epibionts, such as the hederelloids mentioned earlier, and in the Middle Silurian, the first photosymbiotic scleractinian corals that lived in partnership with photosynthetic organisms, made their debut. Despite all this richness, Silurian reefs were inconsistent. In some places, reef fossils are abundant, while in others, they are nearly absent, leaving puzzling gaps in the fossil record. The Devonian period is one of the most fascinating chapters in Earth's long and dramatic story. It belongs to the Paleozoic era, which is part of the Phanerozoic eon, the great stretch of time when visible life became common. The Devonian lasted for about 60.3 million years, beginning roughly 419 million years ago at the end of the Silurian period and ending around 359 million years ago when the Carboniferous period began. It is the fourth geological period of both the Paleozoic and the Phanerozoic. The name Devonian comes from the county of Devon in southwestern England, where rocks from this ancient time were first carefully examined. During the Devonian, the surface of the Earth underwent extraordinary changes, especially on land. Life that had mostly stayed in the oceans was now beginning to conquer the continents. Plants that could release spores into the air, known as free-sporing vascular plants like ferns, began spreading far and wide. Over time, they formed lush, dense forests, creating dark green blankets over much of the land. By the middle of the Devonian, many plant species had developed true roots and broad leaves, and near the end of the period, the first plants that produced seeds, called pteridospermadophytes, or seed ferns, appeared. This major transformation of life on land is part of what scientists call the Silurian Devonian terrestrial revolution. This was not just a quiet spread of mosses and roots, it was a revolution in slow motion, changing the air, the soil, and the entire landscape of Earth. Alongside the rise of plants, the first land-dwelling animals also began to appear. These early creatures were mostly arthropods, invertebrates with jointed legs and hard outer shells. The pioneers included creatures like millipedes, spiders, and early insects, which likely began their journey onto land as early as the Ordovician period. Meanwhile, beneath the waves, the oceans were teeming with life, especially with fishes, which exploded in variety and number. Because of this underwater abundance, the Devonian is often called the Age of Fishes. One group of fish, known as placoderms, had thick armoured plates covering their bodies, and they ruled many ocean habitats. At the same time, cartilaginous fishes like primitive sharks became more common than they had been during the Silurian and late Ordovician periods. A special group of fish called tetrapodomorphs also began to evolve in Devonian freshwater environments. These were the ancestors of all four-limbed animals, including frogs, reptiles, birds, and even humans. Their strong muscular fins gradually began turning into legs and feet, though they weren't quite ready to walk on land just yet. That leap would come much later, in the late Carboniferous period. The Devonian also saw the arrival of the very first ammonites, relatives of modern-day squids and octopuses, with spiral shells and tentacles. At the same time, older marine creatures such as trilobites, brachiopods, and sprawling coral reefs were still thriving, at least for a while. Sadly, the Devonian story took a dark turn. Around 375 million years ago, a devastating mass extinction event struck the oceans. Many of the great reef systems collapsed, jawless fish and placoderms were nearly wiped out, and most trilobites vanished, except for a small group called the Proetida. Another extinction event followed close behind at about 359 million years ago, wiping out even more marine life, including calcite sponge reefs and the last of the placoderms. These twin disasters nearly ended the Age of Fishes and shook the Earth's ecosystems to their core. As for the continents themselves, the Devonian world was shaped by three great landmasses. In the south lay the vast supercontinent Gondwana. To the north was the smaller continent of Siberia, and in between sat the medium-sized continent called Laurussia. Great geological changes were underway. The ancient Rhaic Ocean was closing. South China was drifting away from Gondwana, and a new ocean, the Paleotethys, was opening. Meanwhile, as continents drifted and collided, new mountain ranges began to rise. In North America, this resulted in the Akkadian orogeny, while in Europe, it marked the beginning of the Variscan orogeny. These early mountain-building events would eventually lead to the formation of Pangaea, the supercontinent that would dominate the late Paleozoic. The climate during the Devonian was generally warm, though there may have been glaciers at certain times, especially during the early and middle Devonian. Unlike today, the temperature difference between the equator and the poles wasn't very large. The equator was especially dry, with arid conditions stretching across vast regions. By studying microscopic fossils called conodonts, scientists estimate that tropical sea temperatures in the early Devonian averaged around 30 degrees Celsius, or 86 degrees Fahrenheit. The overall mean surface temperature was probably about 16 degrees Celsius, or 61 degrees Fahrenheit. One of the most important climate changes in the Devonian was a major drop in carbon dioxide levels. The new forests that had spread across the land were pulling carbon dioxide out of the air and locking it into sediments. This led to a significant cooling event in the Middle Devonian, with temperatures falling by as much as 5 degrees Celsius or 9 degrees Fahrenheit. Later on, in the late Devonian, temperatures rose again to levels similar to those in the early Devonian. Interestingly, carbon dioxide did not rise with the warming. Instead, increased continental weathering, the breakdown of rocks on land, likely caused the warming. Fossil plant evidence also supports the idea of a hotter late Devonian climate. These swings in temperature affected the coral reefs too. In warmer times, microbes built reefs. In cooler times, corals and sponges dominated. But by the very end of the Devonian, the planet began cooling again, sharply. This shift ushered in the late Paleozoic Ice Age, a period when vast ice sheets covered parts of the Earth. During the Devonian period, which began around 419 million years ago and ended about 359 million years ago, sea levels were generally quite high. The oceans of that time were full of life, especially in the shallow waters near the coasts. Many kinds of ancient sea creatures thrived during this era. These included tiny tooth-like creatures called conodonts, colonies of filter-feeding animals known as bryozoans, and brachiopods, which looked a bit like modern clams but were actually quite different. There were also mysterious organisms called heterellids, tiny tube dwellers called microconchids, and various types of corals that helped form reefs. Graceful flower-like creatures known as crinoids, which were actually animals related to sea stars, were especially abundant. Although they looked like underwater flowers swaying in the current, they were active feeders. Trilobites, which had once dominated the seas in earlier times, were still present but not as widespread as before. Bivalves, ancestors of modern clams and mussels, became common in deeper ocean waters and on the outer parts of the continental shelves. One of the most exciting developments during the early part of the Devonian, around 400 million years ago, was the appearance of the very first ammonites, coiled-shelled creatures related to modern squids and octopuses. Around the same time, bactritoids also made their first appearance. Both these groups began to thrive and multiply, possibly because the deep ocean had less oxygen than before, which put stress on older groups and opened up opportunities for new ones to take over. Meanwhile, in the world of fish, big changes were underway. Ancient jawless fish, which were covered in bony armour and called ostracoderms, began to fade away. Taking their place were fish with jaws, known as gnathostoms, which were better at hunting and defending themselves. These jawed fish flourished both in the seas and in freshwater rivers and lakes. Among them were placoderms, which were heavily armoured and dominated the early Devonian waters. However, they eventually went extinct near the end of the period, possibly because they couldn't compete with other faster and more efficient fish. Also emerging were the early ancestors of modern sharks and rays, known as chondrichthyes, and bony fish, called osteichthyes. These groups became very diverse and played a major role in Devonian marine life. One of the first well-known sharks, called Cladocelecce, appeared during this time. Because of this explosion of fish diversity, scientists and popular writers often refer to the Devonian as the Age of Fishes. At the same time, marine life that could swim freely in the open water, called nekton, began to multiply and diversify, thanks to the huge number of tiny planktonic organisms floating in the seas. The ocean floor was already crowded with creatures, so more animals began to live and hunt in open waters. This shift toward a swimming lifestyle is known as the Devonian nekton revolution. However, not all scientists agree this was a true revolution. A study published in the year 2018 argued that although the percentage of nektonic species rose between the Silurian and Devonian periods, it actually dropped again during parts of the Devonian, especially in the Praegian age. The study suggested that nektonic diversity wasn't especially high in the Devonian compared to other time periods like the Wenlock to Lockovian, which came earlier, or the Carboniferous to Permian, which came later. Instead of being a sudden change, they believed this growth in swimming animals was part of a longer slow trend across the entire Paleozoic era. Back on Earth's surface, one of the most fascinating structures from this time was a huge barrier reef in what is now the Kimberley Basin of northwestern Australia. This reef stretched for about 350 kilometres, which is around 220 miles. Unlike today's coral reefs, which are mostly built by modern corals and algae, Devonian reefs were built in different ways. Some were microbial reefs, made mainly by ancient cyanobacteria that could carry out photosynthesis. Others were coral stromatoporoid reefs, built by coral-like creatures called stromatoporoids, along with tabulate and rugose corals. During the warm, early and late parts of the Devonian, microbial reefs dominated. But during the cooler Middle Devonian, the coral stromatoporoid reefs were more common. On land, life was changing just as dramatically. By this time, Earth's surface had already been partly green thanks to the mosses and algae that had appeared during the Silurian period. But early in the Devonian, more complex land plants began to appear. These new plants had simple roots and created the first real soils. They were joined by tiny land animals like mites, scorpions, myriapods, such as centipedes and millipedes, and trigonotobids, all of which thrived in this new green world. Some of these animals may have lived on land even earlier, possibly as far back as the Cambrian period, based on ancient track fossils like those of protechnites. One of the most bizarre land organisms at the time was Prototaxites, a giant organism that towered up to 8 meters, around 26 feet tall. It looked like a tree trunk, but wasn't a plant. Some scientists think it might have been a huge fungus, while others believe it could have been a rolled-up mat of liverworts or something else entirely. Insects may have appeared during this time too. Fossils from the early Devonian, around 416 million years ago, include possible early insect remains. As for vertebrates moving onto land, there are fossil traces from the Middle Devonian that suggest the presence of early tetrapods, the first 4-limbed animals that would eventually give rise to amphibians, reptiles, and mammals. However, some scientists think these traces might actually belong to fish digging for food, rather than true land walkers. Most of the earliest Devonian land plants were small, had no true leaves, and spread by spores or vegetative growth. For example, plants like Drepanoficus grew in this way. One of the earliest known plants, Cooksonia, was only a few centimeters tall and had simple branching stems with spore capsules at their tips. A huge milestone occurred during the Middle Devonian, when plants with woody tissues appeared. Fossils of a plant called Amorchophyton chatopanense, dated to about 400 million years ago, show the earliest evidence of wood. Soon after, true trees began to grow, including early types of lycopods, as well as other tall plants like Cladoxylopsids and Archaeopteris, which belonged to a group called progymnosperms. These plants had true leaves and roots, and thanks to a strong material called lignin in their tissues, they could grow tall and resist disease and herbivores. Some of the world's first real forests appeared during the Iphelian Age, made up mostly of these Cladoxylopsid trees. By the end of the Devonian, plants that produced seeds had started to evolve. The rapid development and spread of many types of plants during this time is often called the Devonian explosion, or the Silurian Devonian terrestrial revolution. All this plant growth had another powerful effect. It pulled carbon dioxide out of the atmosphere. This helped to cool the global climate, but it may have also contributed to a major extinction event, as the environment began to change too quickly for many species to survive. As plants with stems, leaves and roots became more complex and began to cover the land in the late Devonian period, a group of ancient creatures known as arthropods evolved right alongside them. These animals, which include early ancestors of insects, spiders and crustaceans, gradually adapted to life on land, finding shelter, food, and a place to thrive in this new world of growing forests and rich vegetation. During this time, something remarkable began. Insects and seed-producing plants started forming close relationships. This early partnership between bugs and plants would eventually shape the modern ecosystems we know today, where bees pollinate flowers and plants depend on animals to spread their seeds. It all began in the late Devonian, a time when land life was just beginning to find its rhythm. As plant life spread and roots dug deep into the earth, soils began to form, and this caused big changes to how wind and water shaped the land. Erosion and the waste sediment was deposited in rivers and oceans shifted. With the land becoming more stable and full of plants and crawling creatures, vertebrates, the first animals with backbones, began to test life on land. By the end of the Devonian period, arthropods had already become fully established in terrestrial environments. But even as life was thriving on land and in the sea, the Earth was heading into one of the greatest extinction crises in its history. The late Devonian extinction wasn't just one event. Instead, it was a series of powerful extinction pulses that struck over millions of years. These occurred at 3 key times: at the boundary between the Gavetian and Frasnian stages, then between the Frasnian and Furmenian stages, and finally near the transition from the Devonian to the Carboniferous period. Altogether, these extinction events are considered one of the big 5 mass extinctions in Earth's long history. The crisis mainly hit life in the oceans, especially creatures that lived in warm, shallow waters. Cool water species were less affected. One of the hardest hit groups were the reef builders, which had created the enormous and beautiful reef systems of the Devonian seas. These ancient reefs, some of the largest the world has ever seen, vanished almost completely. Many other sea creatures suffered terribly as well. Brachiopods, trilobites, ammonites and acritarchs were all seriously reduced in number. Conodonts and bony fishes, two major groups of early vertebrates, lost about 96% of their species. Even more devastatingly, all the ostracoderms, jawless armoured fish, and placoderms, heavily armoured jawed fish, disappeared entirely from the world's oceans. Surprisingly, life on land was not hit as hard. Plants and freshwater creatures, including the ancient four-legged ancestors of amphibians and reptiles, known as tetrapods, survived the crisis. However, some scientists argue that early tetrapods may have come close to extinction as well, though evidence is still debated. The true cause of the late Devonian extinction remains one of science's unsolved mysteries. Many theories have been proposed, but none are confirmed. One idea, suggested by Canadian paleontologist Digby McLaren in the year 1969, is that the extinctions were caused by the impact of an asteroid. While there is evidence of asteroid collisions during the late Devonian, such as the Alamo impact, there is no solid proof of a large enough crater from that time to explain such widespread devastation. The Carboniferous period was a major chapter in Earth's long history. It was part of the Paleozoic era and lasted for about 60 million years, beginning around 358.86 million years ago at the end of the Devonian period and ending roughly 298.9 million years ago, marking the beginning of the Permian period. This period was the fifth of 6 major divisions within the Paleozoic era, and also the fifth period in the broader timeline known as the Phanerozoic Eon. In North America, geologists often split the Carboniferous into 2 smaller time blocks, the Mississippian, earlier, and the Pennsylvanian, later. During the Carboniferous, life on land had become well established. Animals with backbones that had 4 limbs, known as tetrapods, were thriving. These creatures had evolved from lobe-finned fish during the Devonian, and, by the Carboniferous, had developed 5 fingers or toes on each limb, a trait known as being pentadactylous. Because amphibians were so common and widespread during this time, the Carboniferous is often nicknamed the Age of Amphibians. One large group of amphibians called temnospondylls became the dominant animals on land. Even more significant was the first appearance of amniotes, a new group of land animals that laid eggs on land. This group split into 2 major branches, synapsids, which would eventually give rise to mammals, and sauropsids, the ancestors of today's reptiles and birds. At the same time, land-dwelling arthropods such as arachnids, like giant scorpions and spider-like creatures, myriapods, such as the massive millipede-like Arthropleura, and especially insects, including the first flying ones, went through an explosion of new forms and diversity. Towering forests filled with giant ferns, seed ferns, and club mosses covered the land, growing in huge swampy environments. Over millions of years, the remains of these dense forests were buried and turned into thick layers of coal, which is why this period is called the Carboniferous, a name that means coal-bearing. In the later part of the Carboniferous, the Earth went through a period of cooling, and glaciers formed in parts of the southern hemisphere. Sea levels dropped, and the continents slowly drifted together to form a massive supercontinent called Pangaea. Near the end of the period, a minor extinction event occurred, known as the Carboniferous rainforest collapse. This event, driven by changing climate, caused many rainforests to disappear and led to the extinction of several species. For a long time, scientists believed that the level of oxygen in the atmosphere during the Carboniferous was always very high, much higher than today. But more recent studies suggest that oxygen levels actually varied over time. They started out low but then rose sharply, at times reaching as high as 25 to 30%, compared to about 21% today. This high oxygen content may have allowed some insects and arthropods to grow to enormous sizes. The idea of organising Earth's layers of rock into a time system began in the late 18th century. The name Carboniferous was first used in 1799 by the Irish geologist Richard Kirwan. Later, in 1811, it appeared in print as part of a heading by John Ferry Sr. Coal measures, or Carboniferous strata. 4 main rock layers were originally included in the Carboniferous: Old Red Sandstone, Carboniferous Limestone, Millstone Grit, and the Coal measures. In 1822, geologists William Conybeare and William Phillips officially grouped these layers into a Carboniferous unit. Then, in 1835, Phillips named it the Carboniferous system. Eventually, scientists realised that the Old Red Sandstone actually belonged to the older Devonian period. Because rock layers in the British Isles were very similar to those in Western Europe, scientists created a shared European system. The Carboniferous was divided into two major parts: the Lower Dinantian, dominated by limestones, and the Upper Silesian, which was mostly sandstone and shale. The Dinantian was further split into the Tournasian and Visaean stages. The Silesian was divided into the Namurian, Westphalian, and Stephanian stages. In North America, geologists observed a similar pattern but chose to split the Carboniferous into two separate systems: the Mississippian, rich in limestones, and the Pennsylvanian, rich in coal and shale. These two divisions were officially recognized in 1953 by the United States Geological Survey. In Russia, geologists in the 1840s divided the Carboniferous into lower, middle, and upper sections, using rock layers from Russia. By the 1890s, these divisions were named Dinantian, Moscovian, and Uralian. The Serpukovian stage was added to the lower Carboniferous, while the Moscovian and Gelian made up the upper part. Later, the Bashkirian stage was added in 1934. In 1975, the International Commission on Stratigraphy, ICS, officially standardized the Carboniferous timescale. They kept the Mississippian and Pennsylvanian from North America, the Tournasian and Visaean from Western Europe, and the Serpukovian, Bashkirian, Moscovian, Kasimovian, and Gelian from Russian geology. This made earlier terms like Dinantian and Silesian mostly outdated, though some are still used in Europe today. To help geologists across the world agree on time periods, the ICS uses a method called the Global Boundary Stratotype Section, and Point, GSSP. This means picking a specific rock layer at a specific location to mark the beginning of a stage. So far, the Carboniferous system and only 3 of its stages have officially defined GSSP boundaries, because the rocks and fossils can be complicated and hard to match globally. The name Mississippian was first proposed by Alexander Winchell in 1870 based on rock layers seen along the upper Mississippi River. During this time, a shallow sea connected the Paleotethys Ocean with the vast Panthalassic Ocean, allowing sea creatures to spread around the world. This made it easier to match rock layers using fossils. However, there are very few volcanic rocks from the Mississippian, so dating those rocks precisely is difficult. The Tournasian stage, named after the city of Tournai in Belgium, was introduced by André Dumont in 1832. The GSSP marking the start of this stage, and of the entire Carboniferous period, is found in southern France, at a place called La Serre. Scientists initially defined the boundary based on the appearance of a fossil called Siphonoidella sulcata. But later studies showed problems with this method, making it hard to line up the exact timing worldwide. The Visaean stage, also named by Dumont in 1832, is named after the town of Visay in Belgium. Its GSSP is now placed in southern China, based on the appearance of a type of fossil called Eoperastaphela simplex, a kind of tiny shelled creature. This decision was made in 2009. The Serpukovian stage was first proposed in 1890 by Sergei Nikitin and named after the city of Serpukhov near Moscow. It still does not have an officially chosen GSSP. The boundary between the Visaean and Serpukovian stages coincides with a time of major climate cooling and the spread of glaciers. This caused sea levels to drop and isolated many marine habitats, which made species evolve differently in different places, making it harder for scientists to match layers globally. Researchers are still working in places like the Urals and southern China to find the best spot for defining this boundary, possibly using the first appearance of a fossil named Lochria zigleri. The Pennsylvanian period gets its name from the US state of Pennsylvania, where thick layers of coal-rich rock are widely found. This name was first suggested by the geologist J.J. Stevenson way back in the year 1888. During the Pennsylvanian, some major changes were happening on Earth. One of the biggest was the closing of the Reich Ocean and the slow joining of the Earth's landmasses to form the supercontinent Pangaea. At the same time, large parts of the southern continent Gondwana were covered in thick ice sheets. This combination of continental movement and glaciation caused major shifts in climate and sea levels. These changes affected where marine animals could live, making them more localized. As a result, it became harder for scientists to compare rock layers, called biostratigraphic correlations, across different parts of the world. Luckily, the process of Pangaea's assembly also triggered many volcanic eruptions. These volcanic layers can be dated more accurately using radiometric dating, making the Pennsylvanian easier to study than the earlier Mississippian period. Bashkirian stage is the first stage of the Pennsylvanian period. It was proposed in the year 1934 by a Russian geologist named Sofia Semikhatova. She named it after Bashkiria, the older name for the region now known as the Republic of Bashkortostan, located in the southern Ural Mountains of Russia. The official start of the Pennsylvanian and the Bashkirian is marked by the appearance of a tiny fossil called the Conodont declinognathodus noduliferus. This boundary is recorded at a place called Arrow Canyon in Nevada, United States, and was officially recognized in the year 1996. Back then, Arrow Canyon was part of a warm, shallow tropical sea stretching all the way from Southern California to Alaska. The rock layers there show a repeating pattern called a cyclotham, made of alternating shallow marine limestones and sandstones, followed by mudstones and broken-up limestones, showing the rise and fall of ancient sea levels. The Moscovian stage is named after marine limestones and colourful clays found near Moscow, Russia. This stage was introduced in the year 1890 by geologist Sergei Nikitin. Unfortunately, this stage still doesn't have an officially defined starting point, or GSSP, Global Boundary Stratotype Section and Point. In northern and eastern parts of Pangaea, a tiny single-celled fossil called Aljutovella aljutovica could be used to mark the beginning of this stage. However, because it's only found in limited regions, it's not helpful for worldwide comparisons. Other possible boundary markers include the appearance of conodonts like Declinognathodus donetzianus or Idiognathoides postsulcatus. Sites in the Ural Mountains and in Nishui, in Guizhou Province, southwestern China, are being considered as candidates for defining this boundary. The Kasimovian is the first stage of the Upper Pennsylvanian. It was named after the city of Kasimov in Russia and was originally part of Nikitin's Moscovian stage. Later, in the year 1926, A.P. Ivanov recognized it as a separate unit and gave it the name Tigoliferina horizon, based on a kind of fossilized brachiopod. The beginning of the Kasimovian occurred during a time when global sea levels were unusually low, which left gaps in rock layers from that time. This makes it hard to find fossil species that are useful for worldwide correlations. Like the Moscovian, the Kasimovian still does not have an officially chosen GSSP. Possible sites include the southern Ural Mountains, the southwestern United States, and Nishui in China. The Zhilian is the final stage of the Pennsylvanian. It's named after the village of Gel near Ramenskoye in the Moscow region. Once again, Sergei Nikitin defined it back in the year 1890. This stage also lacks a GSSP. Fossils of fusulinids such as Rauserites rossicus and Rauserites stukenbergii are useful for dating rocks in areas like the Boreal Sea and the Paleotethyan region, but they are not found in eastern Pangaea or the edges of the vast Panthalassa Ocean. Scientists are considering sites in the Urals and Guizhou, China, to define this stage more precisely. The transition from the Pennsylvanian to the Permian period is marked by a GSSP located in the Idoralesh River Valley near the city of Aktobe, Kazakhstan. This boundary, officially agreed upon in 1996, is marked by the first appearance of a fossil conodont named Streptonathodus postfusus. A cyclotham is a repeating pattern of rock layers made up of both marine, formed under the sea, and non-marine, formed on land, sediments. Each cyclotham reflects a single sedimentary cycle, beginning with an erosional surface at its base. Though each one may only be a few meters thick, when stacked together they can form sequences that are hundreds or even thousands of meters thick. Cyclothams formed along continental shelves, which were extremely shallow and flat. This meant that even a small change in sea level could shift the shoreline dramatically, either flooding the land or exposing large areas to erosion. The main era of cyclotham formation was during the late Paleozoic Ice Age, which lasted from the late Mississippian to the early Permian periods. As glaciers grew, they pulled water out of the oceans, causing sea levels to drop. Rivers then carved channels into the exposed land and plant roots broke down rocks to form soils. These layers of non-marine sediments formed the base of each cyclotham. When glaciers melted, sea levels rose rapidly, wet lowlands turned into peaty swamps, and thick layers of plant matter built up in these oxygen-poor environments. Over time, this plant material turned into coal. As the seas advanced, they flooded these peatlands, depositing delta, lagoon, and estuary sediments. Eventually, fully marine conditions returned, covering everything with layers of limestone, followed by deep-water black shales as sea levels reached their peak. Although sea levels fell again later, the process was slower and often eroded previous layers rather than building new ones. Because the rise in sea level was so fast, the resulting sediment layers were usually less than 10 meters thick. During the Pennsylvanian, cyclothams were common in shallow tropical seas that covered areas of Laurussia, a region that included what is now the western and central United States, Europe, Russia, and Central Asia, as well as parts of the North and South China cratons. These repetitive sea level changes mirrored the glacial cycles of the late Paleozoic Ice Age. Each cycle followed a pattern known as a 100,000-year Milankovitch cycle, the same rhythm that controlled the advance and retreat of the glaciers on Gondwana. Coal, the dark, energy-rich rock we use for fuel, was formed from layers of dead plant material that built up in soggy, oxygen-poor swamps called peat mires. In these waterlogged places, decaying plants piled up without fully rotting. Over millions of years, this thick, spongy layer of peat was buried under heavy sediments. The pressure and heat from the layers above slowly turned it into coal. Most of the world's coal was created during a very special time in Earth's history, between the late Carboniferous period and the early Permian period. That means most coal on Earth was formed roughly between 323 million and 285 million years ago. The plants that filled these ancient swamps didn't just become coal. They also helped change the chemistry of Earth's air, especially by increasing the amount of oxygen. During the part of the Carboniferous period known as the Pennsylvanian, huge amounts of plant material collected in vast swampy wetlands located near the equator. These lush, low-lying regions stretched across what are now the remnants of the central Pangaean Mountains in an ancient landmass called Laurussia, as well as around the edges of what we now call the North China and South China cratons. During colder times, known as glacial periods, sea levels dropped, revealing wide areas of land that had previously been underwater. Enormous rivers, some several kilometers wide, carved through these newly exposed lands, feeding into networks of smaller rivers, lakes, and swampy peat mires. When the Earth warmed again and the glaciers melted, sea levels rose, burying these wetlands under mud and sand. This cycle of exposure and burial happened again and again for millions of years. Over time, the weight of new sediments pressed down on the buried peat, turning it into thick layers of coal. In other parts of the world, such as Siberia and Western Australia, smaller coal swamps also formed, especially during warmer periods, filled with plants that could survive in more temperate climates. Scientists still debate why Earth saw this dramatic surge in coal formation, specifically during the Carboniferous period. One popular idea, known as the delayed fungal evolution hypothesis, suggests that trees evolved to produce a tough material in their wood called lignin, which resists decay. However, fungi that could break down lignin hadn't evolved yet, so for a while, dead trees and plants simply piled up, creating vast quantities of undecayed organic material. Genetic studies of certain fungi called basidiomycetes, the group that includes mushrooms, suggest they didn't develop the enzymes needed to digest lignin until the Permian period, which came later. But this idea is still debated. Some evidence shows that even by the end of the Devonian period, fungi might have already begun breaking down lignin, even if they weren't yet using the exact enzymes that modern fungi use. Another theory points to Earth's unique geography and climate during the Carboniferous. At that time, many continents were clustered near the equator, where the climate was hot and humid. The land was flat, low-lying, and slowly sinking, perfect conditions for forming endless swamps. This setting, along with very high levels of plant growth and productivity, could explain the massive buildup of peat and the surge in coal formation. This entire period happened during a long stretch of Earth's history known as the Late Paleozoic Ice Age, often abbreviated as LPIA. It was the longest and most intense ice age of the last 540 million years, beginning in the late Devonian period, around 365 million years ago, and ending in the Permian, about 253 million years ago. Temperatures began to fall toward the end of the Devonian. A brief glacial episode happened during the Permian age, just before the boundary with the Carboniferous. This was followed by a short warm period known as the early Tornasian warm interval. After that, more carbon was buried as organic matter, and oceans became low in oxygen, causing the climate to cool even more. This triggered glaciation in Earth's southern polar regions. During a later warm phase called the Vician warm interval, glaciers retreated far back, surviving only in high mountain regions such as the Proto-Andes of Bolivia and Argentina, and the ancient Pan-African mountains of Brazil and Africa. The main phase of the late Paleozoic Ice Age started around 335 million years ago and lasted until about 290 million years ago. As temperatures dropped and carbon dioxide levels in the atmosphere fell, sea levels dropped around the world and enormous glaciers began forming. These icy centres, up to 30 in number, spread across the ancient supercontinent Gondwana, reaching into parts of what are now eastern Australia, northwestern Argentina, southern Brazil, and southern Africa. Scientists believe this dramatic drop in carbon dioxide was caused by the rise of the central Pangean mountains. As these mountains formed and eroded, rocks were weathered, pulling carbon dioxide from the air. The closing of a seaway between the Rheic Ocean and the Tethys Ocean may have also helped cool the climate by changing ocean currents and how heat moved around the globe. Despite the Ice Age, there were still periods of warming. Warmer intervals occurred during the Bashkirian, the late Moscovian, and from the late Casimovian to the middle Gelian, when ice melted, glacial debris disappeared, and sea levels rose once again. During the early Casimovian age, about 305 million years ago, Earth experienced a sudden, intense glaciation lasting less than 1 million years. During this brief cold spell, atmospheric carbon dioxide levels dropped to just 180 parts per million, lower than today's levels. But this cold snap ended just as suddenly when CO2 levels shot up to around 600 parts per million, warming the planet. This spike may have been caused by large volcanic eruptions or a slowdown in the burial of organic matter. The coldest part of the late Paleozoic Ice Age came around the boundary between the Carboniferous and Permian periods. Evidence of glaciers from this time has been found across South America, Africa, Antarctica, Australia, Tasmania, India, the Arabian Peninsula, and blocks of land known as the Cimmerian terranes, showing that huge ice sheets once spread across the southern half of Earth. At the same time, carbon dioxide levels dipped again, down to around 175 parts per million, and stayed below 400 parts per million for the next 10 million years, largely because erosion of volcanic rock absorbed CO2 from the air. To figure out what the atmosphere was like back then, scientists used several different techniques. Some, like trapped gas bubbles in ancient salt crystals, halite, give snapshots in time. Others, like charcoal from ancient wildfires or the presence of certain minerals like pyrite, give broader trends. Charcoal became more common in the fossil record starting in the late Devonian, which suggests that atmospheric oxygen levels were rising. Many scientists think oxygen levels were above 21% for most of the Carboniferous. Gas bubbles trapped in halite crystals from 337 to 335 million years ago suggest oxygen might have been around 15% during the Vician, though this comes with a lot of uncertainty. Pyrite records show that oxygen started around 15% in the early Carboniferous, climbed above 25% during the Pennsylvanian, and then fell below 20% by the end. Though the exact numbers vary, all studies agree that oxygen levels in the Carboniferous rose from around 15 to 20% at the beginning of the period to peaks of 25 to 30% later on. These changes weren't steady. They rose and fell depending on the shift in climate. Some researchers believe these high oxygen levels helped support the giant insects and other large creatures that lived during the Carboniferous, but this idea is still being explored and debated today. As the Earth's climate shifted during the Carboniferous period, these changes were reflected in how sediments were deposited across different regions. In the early part of this time, specifically during the early to middle Mississippian, which spanned roughly from 359 million to around 323 million years ago, the oceans were relatively warm. In these warm, shallow seas, large amounts of carbonate materials, such as limestone, were produced. These carbonates spread far and wide, covering the gentle continental slopes of what are now known as Laurussia, a landmass that included parts of North America and Europe, as well as the ancient continents of North and South China. The geological setup during this time resembled what scientists call a carbonate ramp, a gently sloping underwater landscape where sediments slowly built up layer by layer. Around the coastlines of Laurussia, Kazakhstania, and northern Gondwana, thick beds of evaporate minerals such as rock salt and gypsum were also forming due to the evaporation of shallow seas. But as time passed and the climate cooled, starting in the late Visaean age, which occurred around 330 million years ago, these carbonate-producing processes became limited. They could no longer happen in deep waters and were now restricted to shallower depths, usually less than 10 meters. This led to the development of broad, flat carbonate platforms with steep edges, similar to the kind of underwater cliffs found in today's marine environments. By the time of the Moscovian Age, which began around 315 million years ago, Earth's ice sheets were expanding and shrinking in cycles. These glacial cycles led to the formation of special types of sediment layers known as cyclothems. These cyclothems were made of alternating beds of carbonate and siliciclastic sediments, materials like sand and silt, and were deposited across continental shelves and platforms as sea levels repeatedly rose and fell. As glaciers grew and then melted with the seasons, icy waters flowed along the edges of the Gondwanan continent, bringing nearly freezing temperatures to the surrounding seas. Evidence of this can still be seen today in the presence of glendonite, an unusual mineral that forms from echite, a type of calcium carbonate that only crystallizes in cold water. These glendonites are found in fine-grained marine sediments, indicating the chilly conditions at the time. The movement of glaciers across Gondwana and the rising central Pangaean mountains ground up rocks and produced vast amounts of fine silt-like sediment. Winds carried these tiny particles across the equator, creating widespread blankets of loess, dusty, fertile soil that once covered large areas of what would become central Pangaea. This period of intense glaciation, known as the Late Paleozoic Ice Age or LPIA, was initially seen as a crisis for marine life. Many species disappeared, and for a time, overall biodiversity was low. But newer research shows that this wasn't just a time of loss. The sudden and extreme shifts in climate and environment actually encouraged rapid evolution and the appearance of many new marine species, a phenomenon scientists call an adaptive radiation. The constantly changing climate also reshaped the vast tropical forests of Laurasia many times. Sometimes they were swampy wetlands, and at other times they became dry, seasonal forests. During the glacial episode known as the Casimovian, which began around 307 million years ago, many of the towering tree-like lycopods and other wetland plants declined or disappeared. This drop in biodiversity is closely linked to a sharp fall in atmospheric carbon dioxide levels, which fell below 400 parts per million. While some have called this event the Carboniferous rainforest collapse, it was not the complete end of rainforests. Instead, one type of rainforest ecosystem was gradually replaced by another. As the Carboniferous period gave way to the Permian, around 299 million years ago, conditions became even drier, especially in low-latitude regions. The carbon dioxide levels dropped further, and new types of forests took over. These forests were adapted to survive in seasonally dry environments. Around this time, four-legged animals known as tetrapods also developed new features that helped them live on land, and many new dry land-adapted reptiles, known as amniotes, began to thrive and spread. The land plants of the early Carboniferous period, some of which have been preserved in lumps of coal known as coal balls, were quite similar to those from the late Devonian period before them. But new plant groups also emerged. Among the main plant groups of the time were the equisetaels, giant relatives of modern horsetails, sphenophyllales, climbing plants, lycopodiales, club mosses, lepidodendrales, scale trees, filicales, ferns, medullosales, often called seed ferns, and corditales, an early group related to conifers. These plants continue to dominate the Carboniferous landscape. In the later part of the period, more plant groups appeared, including the Cycadophyta, cycads, Callistophytales, another group of seed ferns, and the Voltziales, early conifers. Some lycophytes from the Carboniferous, especially those in the Lepidodendroles group, were nothing like the small club mosses we see today. These were giant trees, some reaching heights of 30 metres and with trunks up to 1.5 metres wide. They included plants like Lepidodendron, Anabathra, Lepidophlorios, and Sigillaria. Their roots, known by the fossil name Stigmaria, formed thick underground networks. Unlike modern trees, their strength came from a thick outer tissue called the cortex, rather than the inner xylem. Another ancient group, the Cladoxylopsids, were towering plants that eventually gave rise to true ferns. Many fern fronds from the Carboniferous period look so similar to living ferns today that it's hard to tell them apart. Some of these ancient ferns may have even lived on other trees as epiphytes. Fossil records include many types of ferns and seed ferns like Pachypteris, Neuropteris, Alethopteris, and Sphenopteris, as well as tree ferns such as Megaphyton and Caulopteris. The Equisetailers also included the massive calamites, which had hollow jointed stems that could reach up to 20 metres in height and 30 to 60 centimetres in thickness. Another climbing plant, Sphenophyllum, had whorls of narrow leaves and was probably related to both calamites and lycopods. The tall and strap-leaved cordites grew between 6 and over 30 metres high and are thought to be early relatives of cycads and conifers. They bore seed-like structures called cardiocarpus and likely thrived in swampy environments. True conifers like Walchia, part of the Voltziales order, arrived later in the Carboniferous and preferred drier upland areas. Underwater, life was also flourishing. Marine invertebrates were diverse and included foraminifera, corals, bryozoans, ostracods, brachiopods, ammonoids, hederelloids, microconchids, and crinoids. Brachiopods and fusolinid foraminifera became especially abundant from the Vician onward, although some groups like cephalopods and conodonts began to decline. This boom in marine life diversity is known as the Carboniferous' earliest Permian biodiversification event. One of the most common and successful foraminifera of the time was the genus Fusulina, which lived in ancient seas across present-day Russia, China, Japan, and North America. Microscopic shelled creatures like radiolarians have been found in rocks called cherts, from regions such as Devon and Cornwall in England, and across Russia and Germany. Sponges too were common, including various groups like Cotyliscus, Gerticoelia, Chaetids, and the colonial glass sponge Titusvilia. Coral reefs continued to grow, filled with diverse species such as Caninia, Neozophrentis, and Miscellinea. The fan-like phenestellid bryozoans were particularly abundant, including the screw-shaped Archimedes and genera like Phenestella and Polypora. Brachiopods also thrived, some growing as large as 30 centimetres wide, like the giant Gigantoproductus, while others like chonites were smaller and simpler in shape. Other groups such as Aetheridids, Spiripherids, Rhynchonellids, and Pterobrachylids were common too. Some inarticulate brachiopods, like Dicina and Crania, also lived widely. Worm-like annelids, such as serpulites, appear in many fossil layers, while mollusks continue to grow in number and variety. Bivalves like Aviculopecten, Posidonomia, and Carbonicola were common, as were gastropods like Murchisonia, Euomphalus, and Naticopsis. Nautiloid cephalopods became rarer, but tightly coiled nautilids and goniatite ammonoids like Enigmatoceras were still widespread. Trilobites, once abundant, had become rare and were now represented only by a group called proetids. Tiny ostracods, a type of crustacean, were still common, with many genera including Bairdia, Coriolis, and Holonella. Crinoids, often called sea lilies, were especially numerous. Some formed dense underwater meadows, and when they died, their remains created thick layers of limestone. Common genera included Chiathocrinus, Woodocrinus, and Actinocrinus. Sea urchins like Archaeosideris and Paleochinus also lived during this time. Blastoids, which resembled crinoids and had long stalks that anchored them to the seafloor, reached their peak in this period. These included families like Pentranetidae and Codosteridae, showing just how rich and strange the underwater world of the Carboniferous truly was. During the Carboniferous period, an age that spanned tens of millions of years, life both in water and on land was incredibly rich and diverse. Freshwater habitats were teeming with invertebrates. Some of the most common freshwater and slightly salty water animals were bivalve mollusks like Anthraconia, Naiadites, and Carbonicola, which had hard shells and lived in rivers and swamps. There were also many different crustaceans, creatures with hard outer shells and jointed legs, including species like Candona, Carbonita, Darwinula, Estheria, Acanthocaris, Dithyrocaris, and Anthropolaemon. Another fascinating group were the Eurypterids, also known as sea scorpions. These were among the largest arthropods to ever live. Some of them, like Adelophthalmus megarachne, which was once mistakenly thought to be a giant spider, and the massive Hibbertopterus, lived in shallow waters and possibly even ventured onto land for short periods. They were likely amphibious. Occasionally the sea would briefly return to these low-lying swampy areas, leaving behind thin layers of sediment called marine bands. These bands often contain fossils of marine creatures such as Lingula, Orbiculoidea, and Productus, which lived in salty or brackish water. On land, a wide range of air-breathing arthropods also appeared. Fossils of insects, centipede-like myriapods, and spiders, arachnids, have all been found in Carboniferous rocks. These fossils show that arthropods were not only present, but already highly developed and varied. Some of them grew to enormous sizes. One of the largest was Arthropleura, a giant millipede-like creature that could grow up to 2.5 meters long, around 8.5 feet, making it the biggest land-dwelling invertebrate known in Earth's history. In the middle of the Mississippian epoch, roughly in the early part of the Carboniferous, the first winged insects began to appear. Not long after, the skies were dominated by huge predatory insects like the Protodonata, or griffin flies. Among them was Meganeura, which looked like an enormous dragonfly with a wingspan of about 75 centimeters, or about 30 inches, the largest flying insect ever known. Other early insect groups included Syntenopteridea, which were early relatives of mayflies, the plentiful and often large plant juice-sucking Paleodictyopteroidea, the plant-eating Protothoptera, and the primitive ancestors of cockroaches, called Dictyoptera. Many of these ancient insects were discovered in rich fossil beds from places like the coalfields of Saarbrücken in Germany and Commentry in France, as well as inside the fossilized hollow trunks of trees in Nova Scotia, Canada. British coalfields also produced well-preserved examples such as Archaeopteryx, which had large wings with parts measuring over 4 centimeters, or about 2 inches. Some insects, like those in the genus Brodia, still show traces of brilliant colours on their fossilized wings. Interestingly, inside the hollow tree trunks in Nova Scotia, scientists also found early land snails like Archaeozonites and Dendropupa. Meanwhile, the Carboniferous seas were filled with fish, especially the elasmobranchs, a group that includes sharks and rays. Some, like Samodus, had strong flat teeth ideal for crushing the hard shells of brachiopods and crustaceans. Others, such as the Ctenacanthiforms, could grow impressively large. Some, like Cyvodus, may have reached lengths of around 6 to 9 meters, or 20 to 30 feet. There were also sharp-toothed species like the Cimoriida and the Petalodonts, which had unusual circular slicing teeth. Most of the larger cartilaginous fish lived in the ocean, but some, such as the Xenocanthida, adapted to live in the freshwater swamps of the coal forests. Others, like Bandringa, also made their way into inland waters. Among the bony fish, a group called the Palaeoniciformes often lived near the coast but also travelled up rivers. Another group, the Sarcopterygians or lobe-finned fish, included the Rhizodonts, which could grow very large and were likely top predators. Most of what we know about Carboniferous marine fish comes from fossilised teeth, fin spines, and bits of skin armour. Smaller freshwater fish, on the other hand, are sometimes preserved whole. These include species like Kenodus, Euronymous, Acanthides, Chirodus, and Gyracanthus. Around this time, the class of fish known as chondrichthyes, cartilaginous fish, went through a major burst of evolution, especially a subgroup called the holocephalans, relatives of modern-day chimeras. This sudden evolutionary expansion likely happened because, after the extinction of armoured placoderms at the end of the Devonian, many ecological niches were left empty, allowing new types of fish to evolve and fill those roles. One of the most bizarre holocephalans was Stethecanthus, a shark-like fish with a strange flat, brush-shaped dorsal fin covered in tiny tooth-like scales. It's believed that this odd fin might have been used in mating displays. Another curious group was the Eugeniodonts, which developed unique circular tooth whorls in their jaws instead of regular rows of teeth. Among them was the Helicoprionidae, a family of early Eugeniodonts that appeared in the early Carboniferous and became famous for their spiral lower jaws. Even more unusual were the Iniopterygeiformes, a group of holocephalans that looked a bit like modern flying fish. They had enormous pectoral fins for gliding through the water, large eyes, club-like tails and sharp spines on their fin tips. On land, amphibians were becoming more common and diverse by the middle of the Carboniferous. In fact, they were far more numerous and varied than the amphibians we see today. Some of these ancient creatures grew as long as 6 meters. The more advanced land-dwelling amphibians developed scaly skin, which helped them retain moisture. Many early amphibians belonged to groups like the Labyrinthodontia, which had long bodies, bony heads, and rather weak limbs. Some could grow over 2 meters long. Alongside them were smaller amphibians, often only about 15 centimeters long, belonging to a group called Leposponduli. Some of these amphibians, like Loxoma, Eogyrannus, and Proterogyrannus, lived in rivers and were fully aquatic. Others, such as Ophiderpaton, Amphibamus, and Hyloplesian, likely lived both in water and on land. Still others, like Dendropaton, Tuditanus, and Anthracosaurus, may have spent most of their lives on land. However, by the end of the Carboniferous period, the vast tropical rainforests began to collapse, possibly due to a shift toward a cooler and drier climate. This change made life much harder for amphibians, who relied on wet environments to survive and reproduce. In contrast, the amniotes, a new group of vertebrates that included early reptiles and synapsids, began to thrive. These animals had important evolutionary advantages. They laid eggs with protective shells that could survive on dry land, and they had tough, scaly skin and claws that made it easier to live away from water. Among the earliest reptiles was Hylonomus, and the first known synapsid was Archaeothyris. These synapsids would later evolve into mammals and grew rapidly in size and variety during the Permian period, although they would eventually lose dominance during the Mesozoic. Meanwhile, the reptiles, especially the sauropsids, stayed small for a while but later rose to dominate the Earth during the age of the dinosaurs, taking over land, sea and sky until their decline in the Cenozoic era. Toward the end of the Carboniferous, as the climate dried out, reptiles began to spread and diversify rapidly. By this time, amniotes had already split into several groups, including pelycosaurs, early synapsids, proterothyrodids, captorhinids, saurians, and ariosolids, each paving the way for future evolutionary paths. As plants and animals were thriving and growing larger, fungi were also diversifying, especially on land. Marine fungi continued to live in the seas, while on land nearly all modern classes of fungi had already appeared by the later part of the Carboniferous period. During the first 15 million years of the Carboniferous period, there are very few fossil records of life on land. Scientists have debated for a long time whether this gap in the fossil record happened because the conditions were not right to preserve land-dwelling organisms, or if something dramatic truly happened in nature. Recent research suggests that there was a noticeable drop in the amount of oxygen in the Earth's atmosphere during this time. This points to the possibility of a major ecological crisis, or even a partial collapse of the ecosystems on land. This period of change led to the disappearance of certain groups of ancient creatures. Among them were the fish-like ichthyostygalians, early amphibians from the Devonian period that had bodies shaped like fish, but were beginning to explore life on land. These animals were gradually replaced by more advanced types of amphibians. Two important groups began to dominate: the temnospondylians, which were large and diverse amphibians, and the reptiliomorphs, which were closer relatives to the first true reptiles. These newer forms became the most common vertebrates living on land during the Carboniferous. As the Carboniferous period neared its end, the Earth faced another significant extinction event. On land, this is known as the Carboniferous rainforest collapse. Enormous tropical rainforests, which had once stretched across vast regions, began to fall apart very suddenly. The Earth's climate, which had once been hot, moist, and perfect for lush jungles, became cooler and much drier. This dramatic shift is believed to have been caused by widespread glaciation, huge ice sheets forming, and a major drop in global sea levels. With the environment becoming more arid, the rainforests could no longer survive. They broke apart into scattered patches, like green islands in a sea of dry land. The great forests of giant lycopsids, ancient club mosses and relatives that once towered over the land were gradually replaced by simpler forests, mostly made up of tree ferns, with far less variety in plant life. This sudden climate change was especially hard on amphibians. These animals, which were the most common land vertebrates at the time, struggled to survive. Many species vanished, and the variety of amphibians shrank dramatically. However, reptiles began to thrive. They had evolved some key features that gave them an advantage in the drier, harsher world. Reptiles laid hard-shelled eggs, which did not dry out easily, and their scaly skin helped keep moisture in. These adaptations allowed reptiles to spread and flourish, even as their amphibian cousins declined. The Permian period was an important chapter in Earth's ancient history. It lasted for around 47 million years, beginning at the end of the Carboniferous period, approximately 298.9 million years ago, and ending at the start of the Triassic period, about 251.9 million years ago. The Permian was the sixth and final period of the Paleozoic era, after which came the Mesozoic era, starting with the Triassic. The name Permian was first used in the year 1841 by the British geologist Sir Roderick Impey Murchison. He named it after the region of Perm in Russia, where he found distinctive layers of rock during his geological explorations near the Ural Mountains, together with French geologist Edouard de Verneuil. In that area, Murchison noticed an enormous stack of different rocks, like marl, limestone, schist, sandstone and conglomerate, lying on top of older Carboniferous rocks. These new layers were unlike anything previously seen, and that's how the Permian became officially recognised as a new geological period. The name of the region itself, Perm, goes back to an old medieval kingdom called Permia, which once occupied that same land, and is now part of today's Perm Krai in Russia. Before the term Permian was introduced, geologists in Germany used names like Rotliegend and Zechstein for these rocks, while in Britain they were referred to as part of the New Red Sandstone. During the Permian period, the Earth looked very different. All the continents had come together to form one massive supercontinent called Pangaea. This gigantic landmass had formed when Euramerica and Gondwana collided during the Carboniferous. It was surrounded by a huge global ocean called Panthalassa. Inside Pangaea, the climate grew hotter and drier, especially after the collapse of the Carboniferous rainforests, which left behind large stretches of arid deserts. As the environment became harsher, animals had to adapt. Amphibians, which needed water to survive and reproduce, began to decline. In their place rose a new group of animals called amniotes, creatures that laid eggs with protective shells, making them better suited for dry environments. These amniotes eventually split into two major groups, the synapsids, which include the ancestors of mammals, and the sauropsids, which include reptiles and eventually birds. The Permian period was also marked by several waves of extinction, at least 3 and possibly 4, as suggested by different scientists. One major extinction happened at the end of the early Permian, during a time called the Ciceralian epoch. During this crisis, many early synapsids, especially a group often called pelycosaurs, died out, and more advanced forms known as therapsids started to rise. Later, during the Capetanian stage near the end of the Middle Permian, another major extinction event took place. This was likely linked to massive volcanic eruptions in what is now China, forming the Emissian Traps. But the greatest catastrophe was yet to come. At the very end of the Permian, around 251 million years ago, the world experienced the worst mass extinction in Earth's entire history. This event, known as the Permian Triassic extinction, or sometimes called the Great Dying, wiped out about 81% of marine species and 70% of land-dwelling species. It was a truly devastating global disaster. The cause is strongly connected to massive volcanic eruptions in Siberia, which created the Siberian traps, vast layers of lava and ash that released huge amounts of toxic gases and carbon dioxide, triggering climate collapse. Life took a very long time to recover. On land, ecosystems needed 30 million years into the Triassic period to rebuild fully. The naming of the Permian wasn't without controversy. A French-American geologist named Jules Marceau, between 1853 and 1867, found Permian-age rocks across a large part of North America, from the Mississippi River to the Colorado River. He suggested calling it the Diassic period, a mix of Dias and Trias, but Murchison strongly opposed this name, and it was never widely accepted. For many years afterward, the United States Geological Survey refused to recognize the Permian as a separate period. Until the year 1941, they treated it as a part of the Carboniferous period, grouping it with other subdivisions known as the Mississippian and the Pennsylvanian. To organize the Permian more precisely, geologists divide it into three main time blocks, called epochs, listed from oldest to youngest: Cisuralian epoch, Guadalupian epoch, and Lapingian epoch. Each epoch is further broken down into smaller slices of time called stages, which match rock layers from different places in the world. These stages also help scientists match up the timing of rock layers across continents. To make this global coordination accurate, the International Commission on Stratigraphy, ICS, uses something called a Global Boundary Stratotype Section and Point, GSSP. This is a specific spot, usually a rock formation, that marks the beginning of a stage, and is used as the official reference for geologists worldwide. For most of the 20th century, geologists only divided the Permian into two parts, early and late Permian, with the Cambrian stage considered the final stage of the early Permian. But in the year 1992, geologist Glenister and his team suggested that the stages called Rhodian to Capetanian were different enough to be their own distinct middle epoch. This idea was officially accepted in 1999, and since then, the three-part division has been the standard way to describe the Permian. In the past, scientists studying the layers of rock from the Permian period in the oceans mostly relied on fossils of ammonoids, spiral-shelled marine animals related to modern squids and octopuses. However, these fossils are not very common in Permian rocks, and each ammonoid species often lived for many millions of years, which makes it harder to use them to mark specific time intervals. Because of this, experts now use the fossil remains of a different kind of ancient creature, conodonts, to define key time boundaries in the Permian. Conodonts were mysterious, eel-like animals without jaws that had tiny tooth-like structures in their mouths. Although they are long extinct, their hard mouthparts fossilized well and are found in many rock layers from the Paleozoic era and the Triassic period, making them very useful for identifying and comparing layers of rock around the world. The official starting points for each age of the Permian, known as GSSPs, Global Boundary Stratotype Section and Point, are now based on the first appearance of certain species of conodonts in the fossil record. The Cisuralian series, which is the earliest part of the Permian, takes its name from rocks found on the western slopes of the Ural Mountains in what is now Russia and Kazakhstan. The term Cisuralian was proposed in the year 1982 by geologist J.B. Waterhouse. At first it included three stages, the Aselian, Sakmarian and Artinskian, but later the Kungurian stage was also added to match the Russian classification of the Lower Permian. Earlier, in the year 1900, French geologist Albert-Auguste Cochon de Lapeyron had suggested the name Uralian series, but it was later dropped because it was not consistently used. The Aselian stage was named in the year 1954 by Russian geologist V.E. Ruzhenchev after the Asel River in the southern Ural Mountains. The official GSSP for the start of the Aselian is located in the Ideralish River Valley, near Aktober in Kazakhstan. This boundary was officially accepted in the year 1996, and it is defined by the first appearance of a conodont species called Streptonathodus postfusus. Next is the Sakmarian stage, which gets its name from the Sakmara River, also in the southern Urals. This name was introduced by the famous Russian geologist Alexander Karpinsky in the year 1874. The GSSP for the beginning of the Cambrian is found at a site called the Usolka section in the same region, and this boundary was officially approved in the year 2018. It is marked by the first appearance of the conodont species Suitognathes spinodosus. The Artinskian stage is named after the town of Arty in the Sverdlovsk region of Russia. Like the Cambrian, it was named by Karpinsky in the year 1874. As of now, there is no officially agreed upon GSSP for the start of the Artinskian, but scientists have suggested defining it by the first appearance of a conodont species known as Suitognathes affinis wittei. The Kungurian stage is named after the city of Kungur in the region of Perm-Krai. It was introduced by Alexander Antonovich Stukenberg in the year 1890. Like the Artinskian, it still lacks an officially ratified GSSP. However, some recent studies propose marking its beginning by the first appearance of the conodont species Neostreptognathodus penevi. Moving on to the middle part of the Permian, we have the Guadalupian series, named after the Guadalupe Mountains in the states of Texas and New Mexico in the United States. This name was first used in the year 1902 by American paleontologist George Herbert Gertie, based on the thick sequences of marine rocks found in that region. The first stage of the Guadalupian is the Rhodian, named in the year 1968 after the Road Canyon member of the Word Formation in Texas. The GSSP for the start of the Rhodian is located in the Stratotype Canyon in the Guadalupe Mountains, about 42.7 meters above the base of the cutoff formation. This GSSP was ratified in the year 2001, and it is marked by the first appearance of the conodont species Gynogondolella nankingensis. The second stage is the Wordian, named after the Word Formation. It was first used in a formal stratigraphic sense in 1961 by geologists Glenister and Furnish, though the original name was coined earlier in 1916 by Johann August Uden. The GSSP for the Wordian is located in Guadalupe Pass, Texas, in a rock layer known as the Getaway Limestone member of the Cherry Canyon Formation. This GSSP was also ratified in the year 2001, and its base is defined by the first appearance of Gynogondolella acerata, another species of conodont. The final stage of the Guadalupian is the Capitanian, named after the Capitan Reef in the Guadalupe Mountains. The name was originally given by George Burr Richardson in the year 1904, and it was later used formally as a substage by Glenister and Furnish in 1961. The Capitanian was officially recognised as an international stage by the International Commission on Stratigraphy, ICS, in the year 2001. Its GSSP is located at Nipple Hill in the southeastern part of the Guadalupe Mountains. The start of the Capitanian is defined by the first appearance of the conodont species Gynogondolella postserrata. The term Lipingian was first introduced in the year 1923 by a geologist named Amadeus William Grabau, who called it the Loping series after the town of Leping in Jiangxi province, China. At first, it was used just to describe a certain type of rock layer, what scientists call a lithostratigraphic unit. But in 1932, another Chinese geologist, T.K. Huang, expanded its use. He raised the Lipingian to a more formal level in geology, calling it a series that included all the layers of rock from the Permian period in South China that lay above a limestone formation known as the Maoku limestone. Many years later, in 1995, the Subcommission on Permian Stratigraphy, which is part of the International Commission on Stratigraphy, ICS, officially voted to recognise the Lipingian as a global standard in geological time, what is known as a chronostratigraphic unit. Within the Lipingian series there are two main stages, the Wuqiepingian and the Changxingian. These names were first proposed in 1962 by the geologist J. Zisheng. He introduced them as part of the Wuqieping Formation and Changxing Formation, both located in the Lipingian rock layers. The official boundary marking the beginning of the Wuqiepingian stage was set in 2004. It is based on a location called Pengleitan in Guangxi, China. This boundary is defined by the very first appearance of a tiny tooth-like fossil from an extinct eel-like creature called Clarkina postbitteri, which belonged to a mysterious group of jawless animals known as conodonts. The Changxingian stage, on the other hand, got its name from the Changjing limestone, a rock layer that was first described by Grabau back in 1923. This limestone takes its name from Changxing County in Zhejiang Province. The boundary that marks the beginning of the Changxingian is located about 88 centimeters above the bottom of the Changxing limestone in a place called Meishan Section D in Zhejiang. This boundary was officially ratified in 2005 and is defined by the first appearance of another conodont species called Clarkinawangi. To mark the transition from the Permian period to the Triassic period, scientists chose a point at the bottom of a rock layer known as Bed 27C, also in the Meishan D section. This point was accepted as the official boundary in 2001 and is based on the first appearance of yet another conodont fossil, this one called Hindiodus parvus. In Russia, the traditional geological timescale includes a stage called the Tertiarian, which spans the entire Lapingian period as well as the earlier Capetanian and part of the Wordian stages. The stage below that, called the Kazanian, includes the rest of the Wordian and the even earlier Rhodian stage. Meanwhile, in North America, geologists divide the Permian into different stages. The earliest is the Wolfcampian, which itself includes two smaller stages, the Nelian and the Lennoxian. Then comes the Leonardian, which includes the Hessian and Cathedralian stages. After that is the Guadalupian, followed by the Ochoan, which corresponds roughly to the Lapingian used in other parts of the world. In New Zealand, geologists have developed their own timescale for the Permian period. They divide it into three major epochs: the Pre-Telfordian epoch, which isn't divided further, and roughly matches the Aselian, Sakmarian and Artinskian stages; the D'Urville epoch, which is divided into the Makarewan, Waitian and Purahawan stages. This epoch is roughly equal to the Kungurian stage and the Guadalupian epoch; and the Aparima epoch, which includes the Flettian, Barretian, Mangaperian and Telfordian stages. This period aligns closely with the Lapingian epoch. During the Permian period, all of Earth's major landmasses had come together to form a single giant supercontinent called Pangaea. To the east of Pangaea were smaller continental fragments known as the Cathasia terranes. This massive landmass stretched from near the equator all the way toward the poles. Because of this, it had a strong effect on global climate and ocean currents. Surrounding this supercontinent was a vast ocean called Panthalassa, which means universal sea, and a smaller ocean called the Paleotethys, located between Asia and the southern landmass known as Gondwana. During this time, a smaller continent named Cimmeria broke away from Gondwana and began drifting northward toward Laurasia, shrinking the Paleotethys Ocean. Meanwhile, a new ocean called the Neotethys was beginning to form in the south. This Neotethys Ocean would later become a major ocean during the Mesozoic era. As the massive Panthalassa Ocean pushed beneath the southeastern edge of South China, a volcanic chain known as a magmatic arc began to form. This arc stretched all the way to the island of Hainan. The central Pangaean mountains had started forming back in the Carboniferous period, when the continents of Laurasia and Gondwana collided. These mountains reached their greatest height during the early part of the Permian, around 295 million years ago, and were thought to be as tall as the modern Himalayas. However, over time, they were worn down by erosion. Elsewhere, a landmass known as the Kazakhstania block collided with Baltica during the early Permian, which is also called the Cisuralian epoch. By the end of the Permian, several regions, including the North China Craton, the South China block and Indochina, had all fused together and become part of Pangaea. In what is now northwestern Europe, a salty inland sea called the Zechstein Sea existed. This sea had extremely salty conditions and is known as a hypersaline epicontinental sea. Because the interior of such a huge continent like Pangaea was far from the moderating effects of the ocean, it experienced extreme temperatures, hot summers and freezing winters. These conditions also brought seasonal rain and dry spells, similar to modern monsoons. Deserts were widespread across Pangaea. These dry environments favoured the rise of gymnosperms, a group of seed-bearing plants like conifers, cycads, and ginkgos, which can survive dry conditions better than plants like ferns, which need moisture to reproduce. In fact, the first modern-style trees appeared during this time. Some of the most important places in the world for Permian rocks are the Ural Mountains in Russia, which is where the name Permian comes from, regions of China, and the southwestern United States, especially Texas, where bright red rock layers known as the Texas Red Beds are found. The Permian Basin, which stretches across Texas and New Mexico, is named for its deep layers of Permian rocks. It has some of the thickest Permian deposits on Earth. During the very beginning of the Permian, called the Ascelian stage, sea levels dropped slightly. They then stayed relatively high, several tens of meters above today's sea level, through much of the early Permian. But starting in the Rhodian stage, sea levels began to fall sharply. This decline reached its lowest point during the Wuchipingian, when sea levels dropped to nearly the same as they are today. After that, in the Changxingian, sea levels began to rise again slightly. At the beginning of the Permian, the Earth was still locked in an ice age that had started way back in the late Devonian period, more than 360 million years ago, and had continued through the entire Carboniferous period. This icy phase reached its coldest point in the late Pennsylvanian epoch, which was part of the Carboniferous. As the Permian began, the climate slowly started to shift. In the Silurian epoch, which marks the early part of the Permian, the planet began to dry out. This aridification, or increase in dryness, was especially noticeable in regions near the equator, particularly across Pangaea, the giant supercontinent that dominated the globe. At the same time, the melting of ancient ice sheets caused sea levels to rise. Around the boundary between the Carboniferous and Permian periods, a short-lived warming event took place. Although temperatures rose, the climate also became much drier, and these dry conditions continued. However, during the Ascelian and Cambrian stages, both in the early Permian, the Earth cooled again, reaching the peak of the Ice Age. Then, by about 287 million years ago, something dramatic happened. The Artinskian warming event began, and the climate turned warmer once more. The great ice cap over the South Pole started to retreat, but some glaciers still clung to the highlands of eastern Australia, northern Siberia, and southern Africa. This warming also brought even drier conditions, especially in the continent's interiors. Later, near the end of the Cambrian stage, the Earth cooled again, starting a new glacial period that lasted into the early Capetanian stage. Even though it was cooler, the average temperatures were still warmer than they had been at the very start of the Permian. Yet another cooling phase came during the Middle Capetanian, lasting about 3 to 4 million years. This was called the Cambrian event. But this cool period didn't last long. Around 260 million years ago, a huge volcanic eruption occurred in what is now southwestern China, forming the Emishan Traps. The gases and heat from this eruption triggered a sudden warming called the Emishan Thermal Excursion, which helped lead to a mass extinction event in the Capetanian. As the Wuchipingian stage, in the late Permian, began, the leftover volcanic rocks from the Emishan Traps started reacting with carbon dioxide in the air, pulling it out of the atmosphere and causing global temperatures to drop again. By the late Wuchipingian, the long-lasting late Paleozoic Ice Age finally ended, and the last glaciers in Australia melted away. But then came the most dramatic climate event of all, the end of the Permian. At the boundary between the Permian and Triassic periods, a truly massive volcanic eruption took place in Siberia, creating the Siberian Traps. This eruption released more than 5 million billion tons of carbon dioxide into the atmosphere, more than twice the amount that had been there before. This sudden release of greenhouse gases caused a massive warming event, reflected by a sharp drop in oxygen isotopes in ancient rocks. The result was devastating. The Permian Triassic mass extinction, the largest extinction event in Earth's history. Nearly all forms of life were affected, and the Earth entered an intense hothouse state that lasted for millions of years into the Triassic period. During the Permian, the climate was extremely seasonal. A special type of weather system, known as a megamonsoon, formed because of Pangaea's huge landmass and its position on the planet. These massive seasonal winds caused extreme dryness in the interior regions of the supercontinent, while places along the western shores of the ancient Paleotethys Ocean received very heavy rainfall. Scientists have found many pieces of evidence for this megamonsoon. For example, signs of ancient rainforests have been discovered in the Changtang Basin of Tibet, and rock layers in Australia's Sydney Basin show big seasonal changes in sediments, burrows, and fossil patterns. Climate models using modern weather behaviour also confirm that such a powerful monsoon system would naturally develop under the conditions of the Permian Earth. The growing dryness near the equator, especially during the Silurian, was likely caused by the intensification of this global-scale monsoon. The oceans of the Permian were filled with life. There were many types of mollusks, brachiopods, and echinoderms, like sea stars and sea urchins. Brachiopods were especially abundant and diverse, and one group called the Productida made up about half of all known brachiopod genera from this time. These animals even helped shape reef environments as ecosystem engineers. Among the shelled sea creatures called ammonoids, the Goniatitida were common in the early and middle parts of the Permian, but they began to fade away later. Another group, the Prolocanatida, were never very diverse. A new group called the Ceratitida evolved from the Prolocanatida during the middle of the Permian and expanded rapidly toward the end of the period. As for trilobites, only 3 families were still around during the Permian: Prittidae, Brachymetopidae, and Philipsidae. They didn't evolve much early on, but they did experience one final burst of diversity during the Kungurian to Wardian stages. By the final stage of the Permian, the Changsingian, only about 4 to 6 trilobite genera were left. Corals, too, were in decline during the middle and late Permian. On land, the Permian hosted a wide variety of plants, fungi, arthropods, and 4-limbed vertebrates known as tetrapods. Much of the giant continent Pangaea was covered in vast, dry deserts, especially in the northern hemisphere. The heat was so intense that many of the rocks formed during this time turned reddish from iron oxides as the sun baked the bare, plantless land. At the beginning of the Permian, plant life still looked a lot like it had during the Carboniferous. But around the middle of the period, major changes began. The swamp-loving lycopod trees, such as Lepidodendron and Sigillaria, started to disappear. In their place came more advanced seed ferns and the earliest conifers, especially in the dry inland areas. This change happened after the collapse of the Carboniferous rainforests. By the end of the Permian, those ancient swamp plants survived only on a chain of tropical islands called Cathasia, which lay near the equator in what would later become South China. Meanwhile, conifer trees diversified greatly. These included the ancestors of many modern tree families. In the southern parts of the world, vast forests of seed ferns, known as the Glossopteris flora, thrived. The levels of oxygen may have been quite high there. Ginkgo trees and cycads, which are still around today, also appeared during this fascinating chapter in Earth's history. During the Permian period, which lasted from about 299 million years ago to around 252 million years ago, insects, those tiny creatures that had already become quite common in the earlier Carboniferous period, went through a major boom in variety. In the early Permian, many new types of insects appeared, and they began to evolve in all sorts of directions. But by the time the Permian was coming to an end, things slowed down. Both the rate at which new insects were evolving and the rate at which older ones were disappearing dropped significantly. By the beginning of the Permian, something fascinating was already happening, a kind of evolutionary arms race between insects and plants. Insects had started to feed on plants in more complex ways, and plants in turn were evolving defences, structures that helped protect their reproductive parts from insect damage. Fossils show signs of insect bites on ancient plant leaves, and we also find plants with tough outer layers and spikes to keep insects away. Among the most common insects at this time were early versions of group scientists called Paleoptera, Polyneoptera, and Paraneoptera. One major group that had dominated in the Carboniferous, the Paleodictyopteroidea, began to fade away. This was likely because they were facing strong competition from a new group called the Hemiptera, which had similar piercing-sucking mouth parts and lived in similar ways. Another ancient group, the Meganosoptera, which included the largest flying insects ever known, giant relatives of dragonflies, also started to decline during the Permian. At the same time, a very important group of insects called the Holometabula began to spread and diversify. These are the insects that go through complete metamorphosis and include today's beetles, flies, butterflies, and bees. Another group called the Grilloblattidans, now extinct, reached their peak during the Permian. In some places, they made up about 1/3 of all insect species. These odd insects are thought to be distant relatives of modern ice crawlers. Scorpion flies, known as Mecopterans, made their first appearance in the early Permian and became quite diverse by the late Permian. Some of them, like members of the Mesocycidae family, had long tube-like mouth parts, which suggests they may have pollinated ancient seed plants called gymnosperms. The first beetles also showed up at the start of the Permian. These early beetles, such as those from the Firmicupedidae family, likely fed on rotting wood. Later, some beetle groups even adapted to live in water by the end of the Permian. By this time, members of modern beetle groups like Archostemata, Adiphaga, and possibly even Polyphaga had already evolved, the latter being the most diverse beetle group alive today. When it comes to fossils on land from the Permian, the record is somewhat patchy. Fossils from the early Permian mostly come from tropical areas in Europe and North America. But for the middle and late Permian, we rely heavily on rocks from cooler regions like South Africa's Karoo Basin and the Ural Mountains in Russia. In the early Permian, land animals in North America and Europe were dominated by primitive mammal-like reptiles called synapsids, especially the plant-eating Edaphosaurids and the meat-eating Sphenocodontids. Alongside them lived diadectids, early reptile-like creatures, and many amphibians. Small insect-eating reptiles like the Achelystorinids were also common at this time. The synapsids, which are the ancestors of mammals, became more successful and diverse during the Caesarean epoch, the early part of the Permian. One famous member of this group was Dimetrodon, a predator with a large sail on its back. Thanks to their special features, like better temperature regulation and more advanced teeth, synapsids thrived in the dry climates of the Permian and became the top land animals. However, around the time between the Caesarean and the next epoch, the Guadalupian, things started to shift. Amphibians declined, and the older types of synapsids, the pelycosaurs, were gradually replaced by more advanced ones known as therapsids. This change wasn't sudden. It took about 20 million years, from the Sackmarian stage to the end of the Sungrian. As predators and prey evolved, their interactions became more dynamic and complex. But due to gaps in the fossil record, especially during the transition from the Caesarean to the Guadalupian, scientists struggle to piece together exactly how these changes happened. Some experts have identified a period called Olson's Gap, which may reflect a global shortage in fossil deposits. Others suggest that North American and Russian records overlap more than previously thought, and some propose there was even an extinction event during this time, what's been dubbed Olson's extinction. In the Middle Permian, the animal life of South Africa and Russia was dominated by therapsids, especially a diverse group called the Dinocephalians. These creatures went extinct at the end of the Middle Permian during the Capetanian mass extinction. In the late Permian, the animal scene was ruled by more advanced therapsids, like the saber-toothed Gorgonopsians and the plant-eating Dicynodonts with turtle-like beaks. Large parareptiles called Pariasaurs also roamed the land. Another group of reptiles, the Archosauromorphs, distant ancestors of crocodiles, dinosaurs and flying pterosaurs, first appeared and began evolving in the late Permian. Archosauriforms, a subgroup of Archosauromorphs, made their debut right at the very end of the Permian. Cynodonts, which are the direct ancestors of all mammals, also appeared and spread around the globe in the late Permian. Another therapsid group called Therocephalians, like Lycosuchus, emerged during the Middle Permian. Though there were no flying vertebrates yet, some reptiles, such as those from the Vigaltisauridae family, had wing-like structures that allowed them to glide through the air. These gliding lizards are the earliest known vertebrates capable of gliding. During this time, ancient amphibians known as temnospondyls reached their peak in the early Permian Caesarean, but many disappeared in the middle to late Permian, especially after Olson's extinction. Another group, the embolomares, crocodile-like creatures that lived in water, were thought to have vanished earlier, but have now been found in late Permian rocks in China. Modern amphibians like frogs, salamanders and caecilians are believed to have evolved from disaurophoid temnospondyls or lepospondyls during the Permian. Fish diversity during the Permian wasn't especially high. Most of the bony fish belonged to a paraphyletic group called the Paleopterygians, which were not yet part of the modern Neopterygii. The first true Neopterygian fish appeared in the early Triassic, but they likely began evolving in the Permian. Coelacanths weren't very diverse during most of the Permian, but their numbers briefly increased near the end, just before the mass extinction. Freshwater fish mostly consisted of lungfish and Paleopterygians, and lungfish in particular became larger and more diverse in the early Permian before declining later on. Conodonts, a group of jawless, eel-like creatures used to mark geologic boundaries, had their lowest diversity ever during the Permian. Sharks and their relatives, chondrichthyans, are not well understood from this time, but a few groups stand out. Holocephalians, which include today's chimeras, were more diverse earlier in the Carboniferous and Permian, including the strange helicoprion, a shark-like fish with a spiral-shaped tooth whorl. Hybodonts and xenacanthiforms, both shark-like species, were common in freshwater environments and likely ruled those ecosystems. Plant life during the Permian varied across 4 major regions, or floristic provinces: the Angaran, Euramerican, Gondwanan, and Carthasian realms. After the Carboniferous rainforest collapse, the once dominant lycopsid trees gave way to forests of tree ferns in Euramerica. In the Gondwanan region, glossopteridals, tall woody seed plants, dominated for most of the Permian. Glossopteris, the best-known member, is thought to have lived in swampy, waterlogged soil like today's bald cypress trees. Another group of ancient plants, the calumettes, giant relatives of horsetails, grew in dense bamboo-like groves in swampy areas. Fossils from the early Permian Chemnitz petrified forest in Germany show they had complex branches, similar to modern flowering trees. By the end of the Permian, forests with tall, thin trees had spread across much of the world. This global forest expansion is also seen in the widespread fossils of gliding reptiles like the Weigultisaurids. The earliest likely member of the ginkgo family, Trichopites heteromorpha, appeared in what is now France during the earliest part of the Permian. The oldest clear fossils of modern cycads also come from the late Permian. In tropical Carthasia, where it was warm and frost-free, the Noegerathiales, an extinct group of tree-like plants, were widespread. A fossil plant community from this region and time shows a multi-layered swamp forest, with towering lycopsids like Sigillaria, shorter tree ferns, and many Noegerathiales. Conifers, which first appeared in the late Carboniferous, became more widespread and advanced during the Permian, adapting to drier conditions and looking very much like modern conifers. As the world became more arid, especially in the low latitudes, these drought-resistant trees began to take over more and more of the land. The Benetitales, plants that would become prominent in the Mesozoic, also first appeared in China during the Cisuralian. Meanwhile, Ligonopterids, an older group of seed ferns that had faded by the late Carboniferous, still lingered on in some areas of Carthasia and East Gondwana during the late Permian. In the field of paleontology, the Triassic period plays a major chapter in Earth's geological history. It lasted for about 50 million years, starting around 252 million years ago, right after the catastrophic end of the Permian period, and ending about 201 million years ago, when the Jurassic period began. This period marks the first and shortest chapter of the Mesozoic era, often called the Age of Reptiles, and is also the 7th period of the Phanerozoic Eon, the broad span of time that includes all visible life. The Triassic was bookended by 2 devastating mass extinctions, one at the beginning and another at the end, both of which had a profound impact on life on Earth. The Triassic is divided into 3 main parts, or epochs: the early Triassic, the middle Triassic, and the late Triassic. The story of the Triassic begins in the shadow of one of the greatest biological disasters the planet has ever faced, the Permian Triassic extinction event, which wiped out the vast majority of life on Earth. But from this devastation, new life began to emerge and evolve in surprising ways. Fossils from the Triassic show us 3 broad groups of creatures: survivors of the Permian extinction, tough and adaptable; short-lived species that flourished for a while during the Triassic and then disappeared; and long-term winners, like dinosaurs and early mammals, who would go on to shape the future of life for millions of years. During this time, reptiles, especially a group known as archosaurs, ruled the land. Among these archosaurs were the ancestors of crocodiles, birds, and dinosaurs. Though dinosaurs did appear in the late Triassic, they were not yet the dominant force they would become in the Jurassic. Instead, the Triassic world was mostly ruled by pseudosuchians, crocodile-like archosaurs that came in a dazzling variety of shapes and sizes. Some archosaurs even took to the skies, evolving into the very first flying vertebrates, the pterosaurs, with leathery wings stretched between elongated fingers. Before the archosaurs took over, the therapsids, mammal-like reptiles, had been the top land animals during the Permian. In the Triassic, some of them, such as dicynodonts and cynodonts, experienced a brief comeback, but they gradually declined and most vanished by the end of the period. Yet from the cynodonts came a remarkable new lineage, the early mammals, or mammaliomorphs. These tiny, shrew-like creatures were clever and adaptable, and although they remained in the shadows, they survived and would thrive in the next era. Amphibians also had their moment in the Triassic sun. Giant, semi-aquatic predators called temnospondyls survived the end Permian crisis and diversified again. But like many others, they eventually went extinct. Meanwhile, the first members of today's amphibian families, early frogs, salamanders, and caecilians, began to appear and survive the next great extinction. In the water, fish called neopterygians, including the ancestors of modern bony fish, emerged early in the Triassic and spread rapidly. They soon became key players in both freshwater rivers and oceans. During the Triassic, Earth's continents were still fused together in one gigantic supercontinent called Pangaea. This enormous landmass stretched almost from pole to pole and was surrounded by a vast ocean. Because of its massive size, the interior of Pangaea was far from the cooling influence of the sea. As a result, its climate was extremely seasonal, with scorching hot summers and freezing cold winters. Most of the land was dry and desert-like, especially in the centre, where red-coloured sandstones and salt deposits called evaporites formed. Interestingly, while the interior was dry, the polar regions were not icy. Instead, they were moist and temperate, home to forests and even reptiles. There is no sign of glaciers anywhere on Earth during this time. The sheer size of Pangaea also led to powerful cross-equatorial monsoons, giant weather systems so strong they are sometimes called Pangaean megamonsoons. These storms swept from one side of the supercontinent to the other. Though the Triassic was mostly dry, shorter wet periods came and went, especially in tropical areas near the Tethys Sea. Fossils and sediment layers from places like the Svalbard Islands, North America, South China, and Argentina tell us that these humid spells happened several times. The most intense of these episodes was the Carnian pluvial event, a dramatic spike in rainfall and humidity that occurred during the Carnian stage of the late Triassic. It may have helped trigger changes in ecosystems around the world. The early Triassic was one of the hottest times in all of Earth's history. This heat was caused by the massive release of greenhouse gases from volcanic eruptions in an area known as the Siberian Traps. This era began with the Permian Triassic thermal maximum, then dipped slightly into the Denarian cooling between about 251 and 249 million years ago, before heating up again during the latest Smithian thermal maximum around 249 to 248 million years ago. After that came another short cooling known as the latest Olenekian cooling, when temperatures dropped by about 6 degrees Celsius. The Middle Triassic was cooler overall, though it had its own warming episode near the end of the Anisian stage. A more extended cool spell, called the Ladinian-Carnian cooling, lasted from about 242 to 233 million years ago. At the start of the Carnian, global temperatures remained mild, but around 234 million years ago, volcanoes in the Rangelia Large Igneous Province erupted, pumping heat into the atmosphere and setting off the Carnian pluvial event. This led to a warm and humid phase called the Mid-Carnian Warm Interval, which lasted until about 227 million years ago. Following that, the early Nourian cool interval brought another chill from 227 to 217 million years ago, followed by the Mid-Nourian Warm Interval, which lasted until around 209 million years ago. A brief cold snap may have occurred around 214 million years ago, possibly due to the Manicouagan meteor impact. By about 212 million years ago, changes in Earth's orbit caused increased wetland expansion, called paludification, and a shrinking of dry zones. Then came the Ratian cool interval, which lasted from 209 to 201 million years ago. At the very end of the Triassic, the Earth was hit by another extreme heat wave known as the End Triassic Thermal Event. This was triggered by huge volcanic eruptions from the Central Atlantic Magmatic Province, which released vast amounts of carbon dioxide into the atmosphere. The result was the Triassic-Jurassic extinction event, Another great biological crisis that cleared the stage for dinosaurs to finally take control in the Jurassic period. After the greatest extinction in Earth's history, the Permian Triassic extinction, life began to bounce back during the Triassic period, which started around 252 million years ago. But the world wasn't the same. It was hotter, drier, and filled with strange new landscapes. Many living things that had survived the extinction now had to adapt to a very different planet. At the very beginning of the Triassic, a group of ancient spore-producing plants called lycophytes became very common, especially those from a group called isoetals, which includes modern quillworts. The most famous among them was a plant called Pleuromaea, which grew tall and straight like a green column, sometimes reaching up to 2 meters high, about the height of a grown man. These plants thrived in the unstable environment right after the extinction, but as the climate slowly became more stable in the Middle Triassic, they began to fade away. A new kind of seed plant known as the Benneti tails, which had first appeared during the Permian, started to spread widely across the Earth during the late Triassic and became an important part of Mesozoic plant life. In the southern continents that were once part of the giant landmass Gondwana, forests were often dominated by a strange tree called Dicroidium, a kind of extinct seed fern from the group Corystospermales. It was especially common during the Middle to Late Triassic. Meanwhile, ginkgos, a group of plants that now has only one living representative, Ginkgo biloba, started to diversify and spread out. Triassic forests were also full of conifers, which included extinct groups like Voltziales and a family called Caerulopydiaceae, which first appeared in the late Triassic and would later become widespread throughout the rest of the Mesozoic era. Interestingly, scientists have found no coal deposits from the very beginning of the Triassic. This mysterious gap in coal formation is called the Early Triassic Coal Gap, and it seems to be another result of the mass extinction. Theories for this include falling sea levels, acid rain from massive volcanic eruptions in Siberia, global warming that dried out swamps, or the extinction of swamp plants with a long delay before new species evolved that could replace them. There might have even been a sharp drop in oxygen levels in the soil, making it hard for peat, the early stage of coal, to form. In the oceans, a new generation of corals began to grow, although the reefs they made were small compared to the massive coral reefs seen today or in the ancient Devonian period. Around the end of the Carnian Age in what is now South China, these coral communities suffered a sudden crisis. Other marine creatures also appeared or thrived during this time. Serpulid worms showed up in the Middle Triassic, and a group of tube-building animals called microconchids were everywhere. One of the great success stories of the oceans was the return of ammonites, shelled relatives of squid and octopuses, which bounced back from near extinction and began to flourish again. Bivalves, the group that includes clams and mussels, also began to diversify rapidly during the Middle Triassic and became one of the dominant animals in the seas. In freshwater environments, insects started to evolve into many new forms. This was especially important for a group called Holometabula, which includes most of the insect species we know today, such as beetles, flies, butterflies, and bees. In the oceans, rivers, and lakes, fish populations began to recover in a big way. After the extinction, fish species were similar all around the world, what scientists call a cosmopolitan distribution. One ancient group of fish called coelacanths, thought to be near extinction, actually had their highest diversity after the Devonian and were doing quite well in the early Triassic. The group we know today as ray-finned fishes, or actinopterygians, also had a major boom in diversity during the Triassic, especially in the middle part of the period. However, scientists still don't fully understand how this happened, partly because of the poor preservation of some fossils. Among the newcomers were the first members of the teleosts, which are today the most diverse group of fishes. Some ray-finned fish like saurochthydes and bergerids were fierce predators, growing longer than 1 meter and 20 centimeters, that's over 3 feet. In freshwater lakes and rivers, lungfish like Ceratodus were common, mostly known from their strong tooth plates. Another group, the hybodonts, were shark-like creatures that ruled both fresh and saltwater environments throughout the Triassic. One strange group of ancient cartilaginous fish called eugenodontids managed to survive briefly into the early Triassic before vanishing for good. A group of ancient amphibians called temnospondyls survived the extinction, and lived on during the Triassic. The land-dwelling types mostly died out, but the water-dwelling ones lived on. Early species like Tupelacosaurus, Thabancuia, and Micropholis disappeared in the early Triassic, but others like the Stereospondyle did very well, and some even survived until the Cretaceous period. The biggest among them, like Mastodonsaurus, could grow between 4 and 6 meters long, more than 13 to 20 feet. At this time, the first modern amphibians, called lissamphibians, also appeared. The ancestors of today's frogs had already shown up by the early Triassic, but these creatures didn't become common until the Jurassic, after the temnospondyls had mostly disappeared. The reptiliomorphs, a group of early vertebrates that were close relatives of the first reptiles, almost completely disappeared during the Triassic. Only 2 water-loving groups survived, the Embolomera, which vanished early on, and the Croniosuchians, which survived until the end of the period. But in the aftermath of the extinction, a new group of reptiles rose to dominate, the Archosauromorphs. These reptiles had already begun to evolve during the Permian, but the disaster gave them room to explode in diversity. Among them were the Proterosaurs, long-necked, lizard-like creatures. The most famous was Tanystrophaeus, which had a neck longer than the rest of its body. Another family, the Charopterygidae, had long back legs they may have used for gliding. Other archosauromorphs like rhynchosaurs and alicotosaurs were plant-eaters. Rhynchosaurs had big barrel-shaped bodies and beaked mouths with rows of teeth, and were very common during the middle part of the Triassic, but died out around 220 million years ago. Alicotosaurs included animals like Trilophosaurus, with 3-cusped teeth, Pteroterpiton, with a long snout, and the horned Shringosaurus, which was around 3 to 4 meters long, nearly 10 to 13 feet. One important group of archosauromorphs was the archosauriforms, which were fierce predators with sharp teeth and legs placed directly under their bodies for faster movement. Early in the Triassic, big-headed hunters like the erythrosuchids were top predators. Later on, the phytosaurs became widespread. They looked a lot like crocodiles and probably lived in the same way, waiting in water to catch fish and reptiles. But this was a case of convergent evolution. They just looked similar, but were not closely related. True archosaurs, the group that would eventually give rise to dinosaurs, birds and crocodiles, split into 2 main branches early in the Triassic: Avermetatarsalia, the bird line, and Pseudosuchia, the crocodile line. At first, the bird-line archosaurs were not very important in ecosystems, but by the late Triassic they had given rise to pterosaurs, the first flying reptiles, and dinosaurs. The first dinosaurs appeared during the Carnian Age and included small meat-eaters like Colophysis, which was about 1 to 2 meters long. Early plant-eating dinosaurs called sauropodomorphs mainly lived in cooler areas. One mysterious large predator from this time, known as smock, might have been an early dinosaur or a crocodile relative. It's still unclear. Meanwhile, the Pseudosuchians, the crocodile line, were the dominant force on land. This group included armoured plant-eaters called etosaurs, huge meat-eating reptiles called Rowisuchians, and the first small, agile crocodilomorphs. The Rowisuchians were top predators of the Triassic and came in many forms, from giant 4-legged hunters to sleek 2-legged ones with deep sails on their backs. After the Triassic ended, only the crocodilomorphs survived into the Jurassic and beyond. During the Triassic period, the world's oceans were home to a wide variety of fascinating marine reptiles. One major group was the Sauropterygians, which included animals like Pachypleurosaurs and Nothosaurs. These 2 types of reptiles were especially common during the Middle Triassic, particularly in the warm tropical waters of the Tethys Ocean. This group also included placodonts, which had thick bodies and strong jaws adapted for crushing shellfish, and an odd but important early plant-eating marine reptile called a Topodentatus, the earliest known herbivorous marine reptile. Eventually, the first plesiosaurs, famous for their long necks and paddle-like limbs, also evolved from this group. Around the same time, the seas also saw the rise of other marine reptiles like the thalatosaurs, which had long lizard-like bodies. One early example was Askeptosaurus. Another major group was the Ichthyopterygians, which looked a bit like modern dolphins. They first appeared in the oceans during the early Triassic, and soon after, they evolved into many different forms. By the Middle Triassic, some of these ichthyosaurs had grown to enormous sizes, becoming some of the largest sea creatures of their time. Back on land, the first turtles began to appear during the Norian age of the late Triassic period, which was around 220 million years ago. Early turtles like Progonocales and Proterocursis had already developed hard shells for protection. Another group of reptiles, called Lepidosauромorphs, which would eventually give rise to modern lizards and snakes, also began to appear during the Carnian age, a slightly earlier stage of the late Triassic. However, their ancestors likely existed even earlier, possibly as far back as the Permian period. There were also some unique and mysterious reptiles like the drepanosaurs. These small tree-dwelling reptiles had bodies shaped like chameleons, beaks that looked like those of birds, and claws specially adapted for gripping branches. Another group, the Procolophonids, were small, lizard-like herbivores. They were the last surviving members of an older branch of reptiles called the parareptiles, and they continued to play an important role in their ecosystems until the end of the Triassic. Meanwhile, three groups of therapsids, reptile-like ancestors of mammals, managed to survive into the Triassic. These were the Dicynodonts, the Therocephalians, and the Cynodonts. The Cynodont Cynognathes, for example, was a fierce predator and was common in parts of the southern continents, Gondwana, during the Olenekian and Anisian ages of the early and middle Triassic. Among the plant-eaters, the Canamaeriform Dicynodonts and the Gomphodont Cynodonts were especially important, grazing across the Triassic landscapes. The Therocephalians included both large meat-eaters like Moscorhinus and plant-eaters known as boreads, although they eventually went extinct halfway through the Triassic. In the late Triassic, another group of large, fast-moving predatory cynodonts called ectenoniids emerged, and it was during the Carnian age, the early part of the late Triassic, that some advanced cynodonts evolved into the first mammals, marking a major turning point in Earth's history. At the same time, another group of reptiles known as archosaurs was rising to dominance. These included the ancestors of crocodiles, pterosaurs, and dinosaurs. They became the biggest and most successful land-dwelling animals of the Triassic, pushing the therapsids into smaller ecological roles. This shift, sometimes called the Triassic takeover, may have helped mammals evolve. As therapsids and their mammal-like descendants were forced to live in the shadows, literally, they became smaller, more active at night, and fed on insects. This likely led to the evolution of fur to stay warm and a higher metabolism to stay active in the dark. Two remarkable fossil sites from the early Triassic have given scientists an incredibly detailed look at life after the Permian-Triassic mass extinction. These sites are known as Lagerstätten, meaning places where fossils are exceptionally well preserved. One is the Gwiang biota from the Dianarian age, and the other is the Paris biota from the very beginning of the Spathian age. Both of these fossil beds offer precious insight into how life slowly bounced back after the biggest extinction in Earth's history. Another important site is Monte San Giorgio, located today in the area around Lake Lugano, on the border between northern Italy and southern Switzerland. Back during the Middle Triassic, this area was a calm, shallow lagoon protected by coral reefs. The floor of the lagoon had little oxygen, which meant there were no scavengers and not much disturbance. This allowed dead animals to fossilise beautifully, much like in the more famous Solnhofen limestone site from the Jurassic period. Fossils found at Monte San Giorgio include a wide range of marine life, such as fish, and many marine reptiles. These include the commonly found Nusticosaurus, a type of pachypleurosaur, and the strange long-necked reptile Tanistropheus, which may have fished from shorelines with its incredibly long neck. Fossils of land-dwelling creatures such as Ticinosuchus and Macrocnemus have also been uncovered. All of these animals lived during the Anisian and Ladinian ages, which were about 242 million years ago. The Jurassic period was a major division in Earth's history. It began around 201 million years ago, following the end of the Triassic period, and lasted until about 143 million years ago, when the Cretaceous period began. This period is the second and middle chapter of the Mesozoic era, and the eighth geological period of the Phanerozoic eon. It gets its name from the Jura Mountains, where scientists first discovered thick layers of limestone rocks that were formed during this time. The Jurassic started after a massive extinction event at the end of the Triassic. This disaster was likely caused by huge volcanic eruptions from an area called the Central Atlantic Magmatic Province, which released enormous amounts of gas and lava. Another dramatic event happened around 183 million years ago, called the Torsion Oceanic Anoxic event. During this time, the oceans lost much of their oxygen, became more acidic, and Earth's temperatures rose sharply. These changes were probably caused by even more volcanic eruptions, this time from the Karoo-Ferrar volcanic provinces in what is now southern Africa and Antarctica. By the beginning of the Jurassic, the enormous supercontinent called Pangaea had started breaking apart into two giant land masses, Laurasia in the north and Gondwana in the south. The climate during this time was much warmer than today. There were no polar ice caps, and forests even grew near the poles. The Earth had vast dry areas near the equator and lush forests in many other parts. Life on land was changing fast. Dinosaurs, which had already appeared in the Triassic, now became the dominant land animals. They pushed aside other reptile groups and took over most ecosystems. The first early birds evolved from small meat-eating dinosaurs. Other animals that first appeared in the Jurassic include the earliest frogs, salamanders, lizards, crabs, and modern-looking mammals. Mammal ancestors, called mammaliforms, began to diversify. Reptiles called crocodilomorphs started moving from land into water. In the oceans, large marine reptiles like ichthyosaurs and plesiosaurs were common. Flying reptiles called pterosaurs ruled the skies. Modern groups of sharks and rays first appeared and began to spread out. A very important group of modern fish, called teleosts, also appeared near the end of this period. Plants during this time were mostly ferns and gymnosperms, especially conifers, many of which still exist today. A now extinct group called the Bennettitales was also common. The Jurassic climate was generally warm, about 5 to 10 degrees Celsius hotter than today. Carbon dioxide levels were about 4 times higher than today's levels. Even though Earth was warm overall, there were occasional cold snaps, especially in places like northeastern Siberia, where winters could be freezing. The deep oceans were also warmer, and coral reefs grew closer to the poles than they do now. Most deserts and dry lands were located in areas between 40 degrees north and south of the equator. Rainforests and tundra were rare, and ice sheets were probably absent because summers were too warm for snow to build up. Some mountains may have had glaciers though. The climate changed many times throughout the Jurassic. At the very beginning, Earth warmed suddenly after the Triassic extinction. Then came a cooler period between 199 and 183 million years ago, known as the Early Jurassic Cool Interval. Some scientists think there may have been small ice ages during this time. Then, around 183 million years ago, Earth heated up again during the Torsion warm interval, with some parts of the planet reaching 40 degrees Celsius or more. Oceans near the equator reached over 30 degrees Celsius. After that came another cooler phase, the Middle Jurassic Cool Interval, between about 174 and 164 million years ago. Some short-lived ice ages may have occurred during this time. Later, around the Bajocian Age, Europe briefly became more humid before turning dry again. Another possible short ice age happened in the late Bajocian. One of the coldest times came at the Calovian-Oxfordian boundary, where Earth may have entered another ice age. Next came a warmer phase called the Kimmeridgian Warm Interval, from about 164 to 150 million years ago, possibly one of the wettest periods of the Jurassic. Earth's interior became less extreme in its seasonal changes as the Atlantic Ocean began to open and added more moisture to the air. Near the end of the Jurassic, another cooling phase began called the Early Tithonian Cooling Event, which led into the cooler Tithonian Early Barremian Cool Interval, lasting into the early Cretaceous. One of the most dramatic events in the Jurassic was the Torsion Oceanic Anoxic Event, TOAE. It happened in the early Torsion Age, about 183 million years ago, and involved a serious loss of oxygen in the oceans, global warming, and high levels of carbon dioxide. It caused many sea creatures, especially shell-forming animals like brachiopods, to die out. Oddly, marine reptiles were barely affected. During the TOAE, a massive lake formed in the Sichuan Basin, in what is now China. It may have been 3 times larger than modern Lake Superior, and locked away huge amounts of carbon. The oceans became more acidic, which stopped many tiny sea creatures from forming shells. Extra phosphorus in the water made the lack of oxygen even worse, as it caused a feedback loop that intensified the anoxic conditions. The end of the Jurassic is not marked by a clear-cut mass extinction, but it was a time of major change. Some groups of animals grew in number, while others declined. Dinosaurs, which had already started to diversify in the late Triassic, became even more successful and widespread during the early Jurassic. Many new types of theropod dinosaurs appeared during this time, including the earliest relatives of T-Rex such as Proceratosaurus, and strange forms like Limosaurus, a beaked dinosaur that lost its teeth and became herbivorous. Feathered dinosaurs, including early Scansauropterygids with bat-like wings, also evolved. True birds appeared by the middle to late Jurassic, with Archaeopteryx from Germany being one of the earliest known examples. Among the plant-eating dinosaurs, early ornithischians like Lysothosaurus and Heterodontosaurids showed up in the early Jurassic. Later, ankylosaurs, stegosaurs, and other armoured dinosaurs evolved. Some, like Colindodromeus from Russia, had feathers or feather-like coverings. The first members of the horned dinosaur group, called ceratopsians, appeared in China. The biggest land animals of all time, sauropods, reached enormous sizes during the Jurassic. Some were as heavy as 12 tons or more, like Ledumahadi from South Africa. Earlier, smaller bipedal relatives had mostly died out by the Middle Jurassic. Giant sauropods like Volcanodon, Cetiosaurus, and Mamenchisaurus dominated the landscape. By the late Jurassic, groups like Diplodocus and Brachiosaurus had spread across the world. The crocodile-like animals known as Pseudotsuchians had mostly gone extinct at the end of the Triassic, except for the crocodilomorphs, which survived and thrived. During the Jurassic, these animals took on many new shapes and lifestyles. Some stayed on land, others became fully aquatic. One group called Thalattosuchians even developed flippers, tail fins, and smooth skin like dolphins. Another group, the Neosuchians, were the ancestors of today's crocodiles and began adapting to freshwater life. The oldest known Neosuchians might be Calcoiasuchus from Arizona, although its exact placement is still debated. Other ancient crocodile relatives like Razanandron from Madagascar may have been part of a mostly southern group called Notosuchia. The Cretaceous period was a remarkable chapter in Earth's history. It began about 143 million years ago and ended around 66 million years ago. This period was the third and last part of the Mesozoic era, following the Triassic and Jurassic periods. Not only was it the final act of the age of dinosaurs, but it was also the longest period in the entire Phanerozoic eon, lasting for roughly 77 million years. The name Cretaceous comes from the Latin word creta, meaning chalk. That's because a lot of chalky rock was formed during this time, especially in the later part of the period. Today you can still see those ancient chalk beds in places like the White Cliffs of Dover in England. During the Cretaceous, Earth's climate was quite warm, much warmer than it is today. There were no large polar ice caps, and sea levels were so high that vast shallow seas flooded inland areas across many continents. These warm, shallow seas were full of strange and fascinating creatures like ammonites, spiral-shelled animals, rudists, reef-building clams, and marine reptiles that are now extinct. On land, dinosaurs were still the rulers, coming in all shapes and sizes. Dense forests rich with plant life reached all the way to the polar regions. There were even short periods of cooler weather in the earlier half of the Cretaceous, which may have brought brief episodes of ice or snow. Many of the animals and plants we know today can trace their roots back to the Cretaceous. New kinds of mammals and birds began to appear, including the earliest ancestors of placental and marsupial mammals, the groups that would eventually lead to animals like humans, kangaroos, and whales. Some of the first true birds also evolved during this time, developing feathers and the ability to fly in ways more like modern birds. The sea saw the rise of teleost fish, a group that today includes everything from goldfish to tuna. During the Cretaceous, a highly diverse group within them, called the Acanthamorpha, began to flourish. One of the most important events in the history of life happened during the Cretaceous, the rise of flowering plants, also called angiosperms. These plants, which now make up about 90% of all plant species, began to bloom and spread across the world. They started out small in the early Cretaceous, but rapidly took over, replacing the older seed-producing gymnosperms like conifers, cycads, and ginkgos. By the end of the period, flowering plants had become the dominant form of plant life on Earth. The earliest known pollen grains from flowering plants, with just a single groove, have been found in rocks from about 134 million years ago in Israel and Italy. Later in the period, around 90 million years ago, some of the first large angiosperm trees grew as tall as 50 meters, or about 160 feet, with trunks nearly 2 meters wide. Grasses, which are part of the flowering plant family, also appeared during the Cretaceous, with the oldest fossils dating back to the Albian Age, roughly 110 million years ago. Ferns belonging to the group Polypodiales, which make up most modern fern species, also began to spread during this time. Although mammals were still mostly small in size during the Cretaceous, they were very important members of the ecosystem. In some areas, certain mammals called multituberculates were even more common than dinosaurs. These early mammals filled many roles. Some were meat-eaters, others plant-eaters, and some even lived in the water. True marsupials and placental mammals appeared only near the very end of the Cretaceous, but their early relatives were already exploring different ways of living. Dinosaurs, of course, were still the undisputed top predators on land. Many species evolved during this time, including the Maniraptora, a group that includes both birds and their closest dinosaur relatives like raptors, oviraptors, and therizinosaurs. Fossils from places like the Yixian Formation in China show beautiful details, including feathers on many of these animals, offering a stunning glimpse into ancient life. Flying reptiles called pterosaurs were very common in the early and middle parts of the Cretaceous, but their numbers began to fall toward the end. Only a few specialized families, Tranodontidae, Nyctosauridae, and Ashdarchidae, survived until the final years. Insects also had a boom during this time. The earliest ants, termites, and butterflies appeared, along with aphids, grasshoppers, and gall wasps. Some other ancient animals began to fade. Rhynchocephalians, relatives of today's tuatara, disappeared from many regions, likely due to competition from more advanced lizards and mammals. However, they remained common in some southern areas, especially in parts of South America where they outnumbered lizards by a huge margin, 200 to 1 in some places. Another interesting group, the Choristoderes, freshwater reptiles that looked a bit like crocodiles, thrived in Asia during the early Cretaceous. Some had long necks, like the strange Hyphalosaurus, while others, such as the Neocoristodera, looked a lot like modern gharials. By the late Cretaceous, a type called Champsosaurus had spread across much of western North America. These creatures even reached the Arctic thanks to the warm climate. Sadly, the Cretaceous period came to a dramatic end about 66 million years ago, when a massive asteroid crashed into what is now the Gulf of Mexico, leaving behind the enormous Chicxulub crater. This impact triggered the Cretaceous Paleogene extinction event, one of the most devastating mass extinctions in Earth's history. Non-avian dinosaurs, pterosaurs, large marine reptiles, and many other life forms vanished almost overnight. This disaster marks the sharp boundary between the Mesozoic era and the beginning of the Cenozoic era, the age of mammals and of flowering plants, which continue to shape our world today. During the Cretaceous period, the oceans were full of life, and many new sea creatures became common. This was the time when rays, modern sharks, and a group of advanced fish called teleosts were thriving in the seas. Several kinds of large marine reptiles also lived during this time. Ichthyosaurs, which looked a bit like dolphins, were common in the early and middle parts of the Cretaceous, but disappeared during a major ocean event near the end of the period, known as the Cenomanian, Turonian and Noxic event. Another group, the plesiosaurs, with their long necks and flipper-like limbs, lived throughout the entire Cretaceous. Later in the period, giant marine lizards called mosasaurs appeared and became top predators in the oceans. Sea turtles were also present during the Cretaceous. Two groups, Cheloniidae and Panchelonioidea, lived during this time and managed to survive the mass extinction at the end of the period. Today, only one species from Panchelonioidea still exists, the leatherback sea turtle, the largest living sea turtle. There were also flightless marine birds called Hesperornithiformes that swam in the oceans like modern grebes, using their strong legs to dive and chase fish underwater. Among the many shelled creatures in the sea One of the most noticeable was baculites, a type of ammonite with a long straight shell. These creatures lived alongside reef-building clams called rudists, which played a major role in creating underwater reefs. Another important group of bivalves, known as inoceramids, were especially widespread during this period. Scientists often used them to study major changes in ancient life, especially around the boundary between the Turonian and Coniacian ages. There were many carnivorous sea snails, known as predatory gastropods, which used their special mouthparts to drill into the shells of other creatures. Tiny single-celled organisms called foraminifera, especially the globotruncanids, floated in the oceans and became very abundant. Sea urchins and sea stars, which are part of the echinoderm family, also flourished. Small crustaceans called ostracods were everywhere, but interestingly, those species that invested more in reproduction, particularly males, were more likely to go extinct. A mysterious group of crustaceans called Thylacocephala vanished by the end of the Cretaceous. Meanwhile, a major expansion of microscopic algae called diatoms occurred in the oceans. These had glass-like shells made from silica. However, freshwater diatoms did not appear until the Miocene epoch, much later. Another group of tiny marine organisms called calcareous nanoplankton became very important. These helped build up the seafloor and are useful today for tracking environmental changes in ancient seas. The Cretaceous was also a key time in the development of bioerosion. This is the process by which marine creatures drilled into rocks, shells, or hardened seafloors, leaving behind marks that scientists can study. On land and under the oceans, Earth's shape and continents were shifting dramatically. The huge supercontinent called Pangaea, which had begun to break apart during earlier times, finished splitting up during the Cretaceous. The land masses that would become today's continents drifted into their own paths, though they were still in very different positions back then. As the Atlantic Ocean grew wider, a series of mountain-building events called orogenies continued in what is now Western North America. These included the Nevadan, followed by the Sevier, and finally the Laramide orogenies. Gondwana, the southern supercontinent, had started breaking up during the Jurassic period, but its separation sped up during the Cretaceous and was almost complete by the end of the period. South America, Antarctica, and Australia all moved away from Africa, though India and Madagascar stayed connected until about 80 million years ago. This rifting created new oceans, the South Atlantic and the Indian Oceans, and also raised huge underwater mountain chains. These changes caused sea levels to rise all over the world. To the north of Africa, the Tethys Sea began to shrink. For much of the late Cretaceous, a vast inland sea called the Western Interior Seaway split North America into two landmasses, Laramidia in the west and Appalachia in the east. This sea later shrank, leaving behind thick layers of marine rock between coal-rich deposits. In Africa, fossil records show that the continent was also divided by a shallow sea during the Coniacian and Santonian ages. This sea stretched through what is now the Central Sahara and other parts of Central Africa, connecting the Tethys Sea in the north to the South Atlantic Ocean. Another shallow seaway existed between what we now call Norway and Greenland. It connected the Tethys with the Arctic Ocean, allowing sea creatures to move between the two regions. At the peak of these high sea levels, called the Cretaceous transgression, about 1/3 of the land that exists today was completely underwater. The Cretaceous is best known for its chalk deposits. In fact, more chalk was formed during this period than in any other time in the last 540 million years, which is the span of the Phanerozoic eon. As underwater ridges grew and seawater flowed through them, the oceans became rich in calcium. This made it easier for tiny organisms like nanoplankton to build their calcium-rich shells, which settled on the seafloor and formed thick chalk layers. Because of this, rocks from the Cretaceous are well preserved and rich with fossils. In North America, famous examples include the Smoky Hill chalk member in Kansas, which is full of marine fossils, and the Hell Creek Formation, known for its late Cretaceous land animals like dinosaurs. In Europe, important Cretaceous rocks can be found in the Weald region of England. In China, the Yixian Formation has given scientists many beautifully preserved fossils from this time. In the region that's now India, enormous volcanic eruptions formed the Deccan Traps, a vast landscape of lava flows that began erupting in the very last part of the Cretaceous and continued into the early Paleocene.